Cool. So, hello everyone. Welcome to the second edition of the WebAssembly Workshop. I'm Conrad. I am one of the chairs of the WebAssembly Standards body, but I'm here today with my academic hat on to bring you a great selection of talks about mostly the academic side of WebAssembly. But our first invited speaker today is on the industrial side. This is Chris Fallon. He is a senior architect at F5, which is a major, would you say, web company?
Sure, yeah, we'll go with that.
That is using WebAssembly internally for a lot of things and also now pushing some of the standardization work as well. I think that's fair to say. Okay, so Chris, take it away.
Awesome. Yeah, thank you, Conrad. So if we can get my slides. Yep, okay. Cool. So, all right. My name is Chris Fallon. So good morning, everyone. As Conrad said, I'm a senior architect at F5, where I work on many things related to WebAssembly. I'll be giving a talk today about full stack correctness and WASM. So this is kind of a potpourri, a collection of different sorts of correctness, formal verification stuff that I've worked on over the last few years. So let's talk about WebAssembly, right? If you ask anyone what is WebAssembly, it is a secure sandbox. That's maybe its most salient, interesting, distinct property. If I go to webassembly.org and I look at the homepage, I see this bullet point that says WebAssembly is safe. Right, so WebAssembly is a memory-safe sandbox execution environment. Switching gears a bit, if I go to the press release that announced the creation of the Bytecode Alliance, which is a consortium of companies in industry, including my employer, that are working on WASM time and other WASM technologies, this press release says that WASM is secure by default, encapsulated by default, has memory isolation between two modules. Right, so this is the really key core selling point. In fact, if I look at the press release and count words, I see that the word secure is used 12 times. So really secure. Finally, if I look at the headline for WASM time, which is the WebAssembly virtual machine that I work on in industry, we describe it right in the title as fast and secure, strongly focused on correctness and security. And then if I take a random article from industry, or from the industry press, and see how it describes WebAssembly, it offers secure development through sandboxing. I'm just going to pull a few quotes here. It's very secure, it uses sandbox memory, incredibly more secure as a starting point for development, right? So let's focus on that a little bit. When I see that, I get worried, right? So like, this is a great selling point if you think of WebAssembly as a building block and you are building systems on top of it. It is a great promise. But from the point of view of the people actually implementing the technology, it's actually an obligation, right? And it's a fairly scary one because there's kind of not that much in between the sandbox boundary and some really serious security implications. So let's talk about CVEs. Show of hands, who in this room has ever written code that's caused a CVE before? Okay, a few people. So yeah, small club. I hope you don't ever join it. This was one of my two. So about 4 years ago, it was a beautiful morning in California where I live. And I see this message in work Slack channel. Someone says, the daemon keeps segfaulting. This is the daemon that runs WebAssembly on our production servers. And for context, this never happens. The daemon is written in Rust, a memory-safe language. It's very carefully tested. Segfaults just never happen. And faults were coming from inside the WASM code, right? So it wasn't a problem with other infrastructure. We narrowed it down to the actual JIT code that our WASM VM was producing. So one of my coworkers says the fatal words, I'm calling an incident, and we spun up the whole process. And this day got pretty exciting pretty quickly. And so the summary is that this was actually a miscompilation in CraneLift, which is the JIT backend for WASM time, that could cause a WASM instance to be able to access memory outside of its sandbox. And so this is kind of pretty terrifying. So I'm going to actually walk through how this works because it's good background for what I'm going to be talking about in a little bit. So just as context, when you run WebAssembly on a WASM32 on a 64-bit host, typically the way that you do this for performance reasons is that you reserve 4 gigabytes of virtual address space, and you compile the WASM so that its accesses to WASM memory are just offsets from the base. This allows us to catch out-of-bounds accesses with page faults rather than explicit bounds checks, which is a nice performance boon. And so in particular, in a system where you have a bunch of WASM instances running, you'll have a whole bunch of these linear memories, 4 gigabyte regions in a single host address space. So let's look at how a single WASM i32 load instruction is compiled. I'll show the compiler IR first, and then I'll go through some x86 code. So this is just an example here where we might have some arbitrary WASM load, and so we have the base address that's already loaded from some virtual machine data structure. That's v0, that's an i64, that's a pointer and host address space. And then we have v1, which is some arbitrary WASM value, i32. And so we'll extend it to 64 bits, we'll add it to the base, and we'll do the load. Right, so that seems fairly straightforward. We're just accessing an offset from a base, just like an array access. When it's compiled to x86, it might look something like the following. So say we already have the base in RDI. This is an x86 register. We'll have some instruction. Let's just say, for the example, that it's an add that produces the i32 in WASM. So that's the add ECX from something. So that's our actual WASM guest address. And then we'll add it to the base, and we'll do the offset, and we'll do the load from the offset. And so an interesting semantic detail here of the x86 instruction set, when it was extended to 64 bits, is that writes to the 32-bit name for a register, so ECX rather than RCX, actually implicitly zero extend to 64 bits. And this is nice for a number of reasons, but one thing that it gives us is that we can actually elide this zero extend operator, right? So we can know that, okay, this value happened to be produced by a write to a 32-bit register. It was automatically zero extended, so I can just add that directly to the base. Okay, so that's the code that we have. One other thing to know about the way that we produce code is that we're an optimizing compiler, which means that we don't produce the instructions directly. We actually produce virtual register code and then run register allocation. So we don't actually name the registers. We just have register 0, register 1, whatever, and then the register allocator assigns actual registers to those names. And the register allocator is allowed to insert spills and reloads between any two instructions. And it might need this because we might have more live values than we have registers, needs to move values around to prepare for any instruction. And so you might actually spill and reload this ECX value. So that's fine. That preserves semantics, right? We write it to some slot in memory, we load it back, everything is fine. However, we also might want another optimization, which is that when we compile code down to machine code, we have the IR type. So we might have a 32 or 64-bit value or a float 32. The register that it lives in might be wider than that value, right? So an example could be that F32 actually lives in an XMM register, which is 128 bits wide. So you might not want to spill and reload that entire datum. You might actually just want to have the narrow value spilled and reloaded. So rather than RCX, we might just spill and reload ECX. You might start to be seeing where this is going. Okay, so to start to put the pieces together, we have an optimization where we elide 32 to 64-bit zero extends because they happen for free on x86. We also have an optimization where we spill only the actual value width. And so really the core bug here is already on the screen, which is that we are using the upper bits of the register when they're technically undefined. So we map narrow values to wider machine registers by saying the upper bits are undefined. So we did not reflect that in the IR type. Right, but then there's one other thing that's sort of the icing on the cake that made this a really exciting CVE. So if we just had this code, it would actually still be fine. We would have gotten lucky because the load back into ECX would have still zero extended. But when we wrote the code, when I wrote the code, I should say, it's my fault. For some reason, I still don't know why, maybe a copy-paste mistake, I did a sign extending load rather than a normal load. And so the effect of this is that we would spill a value, we would load it back, the upper bits would turn from zero extended to sign extended. And that happened in the middle of the sequence that assumed that it was still zero extended. And so the effect of this is if you had a WASM address above 2 gigabytes, it would actually become negative. So 3 becomes negative 1 gigabyte, which is really exciting when you have a host memory layout that looks like this. One guest gets to access another guest memory. So contrary to that meme, this is actually not fine, right? Okay, so the aftermath of this was kind of as you would expect. We did an emergency version bump. We did a patch release. This was actually kind of a good forcing function for our CVE process in Bytecode Alliance. We hadn't really developed a lot of the details of this, so we're much better now. Of course, we hope that it never happens again, and so we started asking questions, how can we ensure this never happens again? I'll put an asterisk on the word again, because it turns out it did happen again. This one was also my fault. And so I won't go through the details of this one. Basically, we flipped a U extend and a left shift, and you could control some bits above 32. It was not good. Right? And so like this is great for verification researchers, but the fact is that we're human, and so this is going to keep happening. And so we need to ask like, can we do better? Are there ways to do better? So actually, one thing I want to talk about is why are we even in this mess in the first place? In particular, why do we trust the compiler, right? So we have pretty nice abstractions like virtual machines or even processes on a multi-processing operating system that are very strong and well-tested isolation boundaries. So why not just use those? So it actually goes back to this paper from SOSP 93, which introduced SFI, software fault isolation. And so the idea here is that in some circumstances, when you have a whole bunch of distinct trust domains that want to rapidly either call each other directly, so actually interact, or you're just time slicing between them, you actually don't want to pay the context switch overhead if you're using processes, for example, or separate address spaces. So it actually makes sense to pay the slight overhead of the instrumentation handled by the compiler in order to do the isolation compiled in software. And this is a system design trade-off, right? And so you might say, okay, well, you know, that's kind of a niche thing. You have a whole bunch of WASM instances in one process. But actually, this is kind of essential for many workloads, not just server-side, where we have very dense multi-tenant with many different trust domains in one process, but at the browser as well, right? Wants fast WASM to JS interaction. And so when WASM calls JS and JS calls WASM, that's also kind of crossing the SFI boundary. And so this is actually, I would argue, one of WASM's secret superpowers. And actually, there's a blog post by Lynn Clark and the Bytecode Alliance blog called that describes this as nanoprocesses. It's like a really powerful building block to have these extremely tiny virtual or trust domains, virtual machines essentially, that you can put inside of a process. But in order to have them, we have to trust the compiler, right? And so that's the problem we need to work on. Okay, so how do we write a correct compiler? Well, we do a lot to try to ensure correctness. So I'll just walk through like, you know, we do all best practices. We do differential fuzzing against the WASM spec, against different WASM implementations, V8, WASMI. We do actually symbolic translation validation of register allocation and fuzz with that. If I have time, I'll talk a little bit about that. We do chaos testing, so we like perturb the compiler and make it do different semantically valid but weird things. We also let the compiler backend, CraneLift, be used as a Rust backend. So that's kind of trial by fire, compile the entire world in Rust and you find bugs. But somehow we still find these CVEs. And if I extrapolate from these two data points, I don't have a line, I can say that they happen once every other year, right? So that's still not that great if this is if this is the only thing between us and a data breach. So I would simply prove the compiler correct, right? How hard could it be? So actually, that's kind of what I did, or what I'm trying to do, I should say. I have not, and by any means achieved this. So let me outline what the anti-goal is first. So there are actually two well-known projects at least. There may be others that I'm not aware of, which is to prove an entire compiler correct from end to end ahead of time for all inputs, right? So there's CompCert for C, there's CakeML for ML. And these are extremely impressive projects, don't get me wrong. But they were started from the beginning, at least as far as I understand, with the goal of being a verified compiler. And that sort of trickles through all of the other decisions that they make at an engineering level. And so they're engineered from scratch. We have 200,000 lines of existing code that we're not going to rewrite. They also limit, to some degree, the optimizations that they do because they have to be proven correct, right? There are some code transforms that we as humans can reason informally about or just know work, but are quite hard to do a machine-checked proof for. And then finally, it's an enormous manual effort. We can't afford an engineer century as a 5-person open source project. So okay, let's narrow scope a little bit. And there are maybe two ways we can do that. We could verify a part of our compiler completely for all inputs, right? So let's pick a phase, maybe instruction selection. Or we could verify certain limited properties of our compiler end to end. And so I'll actually talk about both. For the first time, I'm going to crib the work that my collaborators and first authors did much more than me. But I'm going to talk about work that we published this past year at ASP+, just very briefly. And then the second part, I'm going to talk about proof-carrying code, which is kind of ongoing work. So we're going to talk about that, and then if I have time, which I might not, I'll talk about guest code correctness as well. So let's talk about instruction lowering. What is instruction lowering? So in a compiler backend, you have an IR, and you want to produce machine code. Maybe the most interesting part of that mapping is that you actually pick the machine instructions that correspond to the IR opcodes or the IR instructions. And this is a fairly intricate problem that has a lot of domain knowledge encoded, and you want it to be good because you want good instruction selection. You want to produce good code. And so there are a lot of like clever tricks that end up happening that mean that this is very fertile ground for bugs. And so about 4 years ago, I designed a DSL that we call ISLE that we use in CraneLift that is used for us to express the lowering rules from the IR to machine code. And right at the very beginning, I actually put this paragraph in this RFC that I wrote describing the design, where I was thinking about verification, and I didn't really know exactly how it would work, but I was at least signposting, okay, we probably want this at some point. And so it's a term rewriting system, and so I sort of designed it to be hopefully amenable to that. A few months after that, I wrote another RFC in Bytecode Alliance. I was tech lead of CraneLift at the time, so I wrote a roadmap for the next year. And I said in the next year, we should attempt to find some concrete ways to do formal verification. A few weeks later, I got emails separately from two academics, Alexa Van-Haddam and Fraser Brown, who are both my excellent collaborators now. And so they both wanted to work on this. And so we started up a collaboration. And it turned into this in ASP+, right? So that was pretty cool. So I'm going to describe sort of how it works. Let me show you a rule in ISLE. So this is a simplified example of like the simplest possible instruction selection case that you could have, which is that we have an IR opcode, rotate right, rotor, that maps directly to an AR64 instruction that's also called rotor. So super easy. All we have to do is map the opcode to one instruction. And so the way that we might verify this, you could imagine, if we're using an SMT solver like Z3, is that we would have a theory of bit vectors formula for the semantics on the left-hand side and the right-hand side. And we would then just ask the solver, are they equivalent? Or if not, give us a counterexample. So that's actually kind of a high-level sketch of what we did. But there's a lot more that you need to do to make this work. And the reason that it gets a little more interesting is that in a real system, we don't just have sort of this cartoon term rewriting where we go directly from the terms on the input to the terms on the output side. We actually have a lot of what we call helper terms. So here I'm showing slightly more detail, still a lot elided, but we have this helper term that we call hasType. It's actually a virtual term, so it calls into Rust. It doesn't actually exist in memory. And if you expand the call graph, or the rewriting graph, I guess, there are like a bunch of levels. I won't go through all the details here. Similarly, on the right-hand side, there are a whole bunch of levels to the term rewriting, down to something we call put-in-reg, which maps an SSA value to a machine register. And so it's actually not as simple as just saying, here are the semantics here are the semantics here, prove them equal. We have a whole bunch of terms, right? And so what we ended up doing, and the thing actually I didn't mention is that we don't ever materialize these terms in memory, so it's not actually a rewriting system from a concrete tree of terms you can dump here and here. These terms actually bottom out in FFI into the rest of the compiler, which is written in Rust. So they're virtual terms. And so at some level, we have to sort of like draw a boundary and say, we have a reasonable spec at this interface. This is actually the IR interface, and the rest is just glue that we're going to ignore for now. And so what we did is we drew that boundary on both sides, something that looked like the IR, something that looked like the machine instructions. And then we attached these spec forms to every helper term, basically. And the way they work is that they provide certain SMT formulas, given that certain formulas are true, right? So it's an implication. It's precondition, postcondition, standard verification stuff. And there's a lot more that actually is needed to make this work. That I won't talk about for time reasons. We have to handle type polymorphism. The rules work for different widths. There's a lot of stuff that makes that tractable. But the upshot is that it actually does find real bugs. So it hasn't found a CVE yet. I hope it never does. There's kind of a conflict of interest here. I don't want to write CVEs, but then I do for this project. But it has reproduced the CVEs that we found. And it's found some other interesting edge cases that we don't consider CVEs, but are still compiler bugs, especially with narrow values, end up being pretty tricky. And so there are ongoing discussions. The thing I want to highlight here is that this is not just a once and done academic project that verifies a snapshot. There are ongoing discussions in how to make this scalable in terms of runtime, and then easy to use, such that we can actually incorporate it into our CI. And have it part of our normal developer workflow. So the holy grail, the end goal, is that we have our open source project on GitHub, and someone does a PR to add a new instruction selection rule, and we can actually know right then and there if the SMT solver likes it or hates it, and if it hates it, how do we prove it correct, or how do we fix the bug? and give us a counterexample, etc. Right? So that'd be great. Okay, but can we verify something end to end? So here's a high-level view of the CraneLift compiler pipeline. So we start with WASM bytecode. There's a translator to CLIF, the CraneLift intermediate format, which is our IR. There's an optimizer that goes CLIF to CLIF. Then instruction selection, which is what I just talked about, that goes to virtual register code, vcode. And then there's machine code at the back end. So we verified, kind of, it's in progress, the instruction selector. I'll talk more about the register allocator later. We do translation validation there. But what about the other two phases? Those are large bodies of code, especially the optimizer also has a lot of cleverness embodied in it. And then there are also integration and glue bugs, right? So there's the thing where you verify every individual phase, but the assumptions that they make at the boundaries are not exactly lined up. For example, yes?
Yes. So the bug you showed earlier was an optimization on the assembly level, right?
Yes.
So where does that fit into this pipeline?
So that would actually have to do with the way that the register allocator is integrated. One of two things. It's either the move sign extend is at the register allocator level. It's also the instruction lowering that assume the wider type is at the instruction selection level. So we do, in principle, have the pieces that we would need to resolve that. For practical reasons, we actually verified AR64, not x86, so we haven't actually reproduced the 2021 CVE yet. But in principle, we could. Yeah.
Okay, thanks.
Okay. So what about integration glue bugs? Can we get something that's actually end to end and that we actually feel good about? So proving the entire compiler correct is hard, right? C compcert, C CakeML. Can we actually prove something much narrower, namely that all memory accesses in the machine code are to valid data structures, so are to either the sandboxed memory or are to VM, like VM context structures? And the way we might do this is we might build an independent checker that operates on the machine code after the compiler is done, right? So the compiler is not trusted at all. It's not part of the trusted computing base. We're just verifying that its output conforms with our expectations. It turns out this has also been done. This was some of my collaborators, but before my time, I was not involved in this work. This is VeriWASM, right? So that Russian there means trust but verify. So trust but verify, SFI safety. And it actually works on CraneLift, which, cool. So maybe we have something we can use. Unfortunately, it was written to work on CraneLift, but another WASM runtime that uses CraneLift, which is now end of life, called Lucid. And so at the time, that was sort of one of the leading options, and so that made sense, but now WASM time has kind of taken over. And then it also operated on a much older version of CraneLift, which was sort of poorly optimizing, which makes the problem easier for the verifier, but anyway, so we'll talk more about that. Okay, so VeriWASM actually verifies multiple properties, stack safety, a bunch of other stuff. We'll talk about the WASM heap here. I want to give the key idea here, and then we'll sort of talk about what I think we're going to do to extend it. And so the key idea with VeriWASM is that it's an abstract interpretation. They define a lattice that's focused on essentially what the memory sandboxing code does. So there are different states that represent the different pieces that have to come together. So here we have some code that has a heap base and some register. We have some I32, and then we're going to add the base to the add the I32 to the base, and then access the offset. So you can imagine that we would have a lattice value that in our abstract interpretation that represents the heap base. We might have another that represents a bounded 4 gigabyte value, right? So this is a value that's been 0 extended from 32 to 64, and is from 0 to U32 max. And then we could define operators over our abstract domain, such as addition, that would take heap base plus bounded 4 gigabytes and would tell you that that's a valid heap address. So if you load from that, that's a valid load. And so you can imagine building a checker in this way. And it would work, and in fact it did. That was the 2021 paper. So actually, after our CVE in April 2021, around May, I took a look at this and wondered, could we update it to work on modern CraneLift and WASM time? And so I actually did do an update to WASM time, but for a very limited domain, so one memory only, no dynamic bounds checking. We found that I had about 30% compile time overhead, which for an academic work is actually fantastic, right? But at the time at my employer, we had very limited control plane resources, and we actually could not afford that. And so we opted not to deploy it. So it just kind of was shelved and sat there. And then the 2023 CVE came along, and I started thinking again, like, okay, we really need this. It would be really great if we could find a way to make this work. And at the same time, CraneLift and WASM time had both advanced significantly in the features they supported and the optimization strength. And so there was a question of how are we going to actually make it work for more complicated code that is more optimized. So let me talk about what some of the differences are, and I'll actually talk about multiple memories and tables. So Lucid, actually, the earlier WASM VM that VeraWASM worked on, had a very simple memory model. Its data structure was basically a single heap in one direction, and VM context, so WASM globals and some other miscellaneous state, in the other direction, from a single pointer. And that single pointer was held in a pinned register. It was always the same register in machine code. And so that actually is what enabled that lattice-based approach to work fairly well, is that the code was of a fairly restricted shape. On the other hand, WASM time is a little more flexible. So first of all, we do register allocations. We don't have a single register that's pinned. We allow the register allocator to move the pointer to the VM context around, spill it, reload it, so already we see we're gonna have to track that movement. We also support multiple memories, and we support different kinds of memories, so there's a level of interaction with memory descriptors. Some of these memories are not bounds checked, some of them are. And we have shared versus non-shared memories for WASM threads, all sorts of interesting edge cases where we have optimizations that produce different machine code that we would have to handle in this analyzer. And also the optimizer got better. Yeah, that created a lot of problems. So let me talk about what we want in the perfect verifier. We want linear time and space verification, and this is actually something that WASM itself, core WASM, focuses on as well, right? When you load a WASM module, you want to know that you have, you don't have the possibility of denial of service with an untrusted WASM module, causing the verifier to run for example, quadratic time. So let me talk about how that doesn't happen if we do sort of a naive approach. So I'm showing some machine code here with 3 different accesses to 3 different memories, a static memory and 2 bounds checked memories, and I'll walk through which part is which. So first we compute some arbitrary I32, and then this move RBX, this load into RBX, is a load from a 4 GB memory that's statically bounds checked. So there's no bounds check in the machine code, it's just the virtual memory tricks. And then we have a dynamically bounds checked memory where we compare RAX, the address, to R9, which is some other memory bound that we've loaded before. And this is spectre safe. We deal with spectre mitigation, so this is a conditional move rather than branch. We basically move 0 in if it's out of bounds, and we do that again, right? And so we actually have 3 different conditions on RAX here. If we were to try to describe this in some value in a lattice, we might have to have some expression like this. It's less than 4 GB statically. It's also less than R9. It's also less than R11. And so you can see how if the optimizer starts to merge together these different accesses and merge the pieces together, we end up getting a very complicated analysis domain where we're deriving a whole bunch of facts that are unnecessarily merged together, and this can cause quadratic behavior fairly trivially, right? And so we're in an environment where we don't trust the user input. We're trying to compile and run the code, but we don't trust the producer of the code, and so we can't have this. This is a denial of service vector. And then there's also the complexity here where we have 2 separate pieces that have to be combined later. So we have the compare and the cmove, and you play a lot of tricks getting the lattice like just right, and it ends up being very brittle. We also want this to be portable, so we have x86 and ARM. We don't want to have too much that's architecture specific. Basically, we just want semantic descriptions of what the instructions are, and that's it. We want to be able to keep it up to date, right? So adding optimization shouldn't be too hard. And we want to prove the safety of all loads and stores. And then we want it to be fast enough to run in production, right? So just a few requirements. How hard could this be? Okay, so because this is a workshop talk, I'll tell you this is a work in progress. I've tried like 4 different approaches. I'm on my 5th. I think number 5 is going to be the lucky one. But what does work is that this does actually work for multiple static memories in modern WASM time and crane lift, over WASM time data structures and all crane lift optimizations turned on. And it has 1% compile time overhead, which is pretty fantastic. So it's still kind of like it needs to be fuzzed, it needs to be productionized a little more, but at some point this year, I want to try to get this turned on. And so, yeah, I won't talk about the different approaches I took that didn't work. Right, okay, so what is the key idea here? It's proof carrying code. So this, again, is an old paper, actually, from POPL' in '97. And the key idea with proof carrying code is that the compiler itself will give you a proof that says this is why the code satisfies certain properties, right? So instead of having this analysis that has to derive all possible facts and then try to put them together, PCC will say, I'm giving you exactly the breadcrumbs that you need to follow, and the checking is much cheaper than the from-scratch analysis. So think of it kind of like typed assembly, which is a related work. And so I'm just going to show you, for time reasons, I'm just going to show you a very brief overview of how this works. So this is IR from CraneLift. This is Cliff. And the important and interesting things to note here are the bang expressions. So I have GVs, which are global values. These describe the VM data structure. So VM context, field on the VM context. And then below we have the SSA, IR, and we have values that are basically loading the memory base and then adding the base, or adding the offset to it and then doing a load. So the bangs basically describe what we call facts in the PCC system, but you could think of them as types as well. And so basically we say that the first argument is actually a pointer to MT0, which is a memory type, and it's offset 0. So the two numbers are min and max offset. We have a range. So this is an absolute offset of 0 into something that is memory type 0. And memory type 0 is a struct. And we're not going to tell you everything about the struct because we don't actually need to use this for compilation. We only need to tell you what you need to know to verify the facts that we give you. And so the struct here is basically saying that it's 88 bytes, so we allow any load within the first 88 bytes offset. And then we have a field at offset 80 that has another fact attached to it. So if we do a load from that field, we get to verify and use that fact. And so we verify that when we do the loads. We also have facts that describe ranges, right? So if we have a uextend from 32 to 64, we know that that value is going to be between 0 and U32 max minus 1 inclusive. And so that's going to verify. And then we can basically define abstract domain add operations on these facts, just like we did in the lattice for VeriWASM, and say that if we have a memory type 1 offset 0, and add offset 0 through U32 max minus 1, we can add the ranges, and know that this is a pointer to memory type 1 somewhere in that offset range. And then we know that MT1 is a memory that has that valid amount of space, right? So it's a 6 gigabyte reserved virtual memory space, so allow any load or store within that range. And so then when we have the checked flag on a load, we actually check that the address has the necessary fact, and we reject this code if it doesn't. So there's some stuff with dynamic bounds that actually I won't go too much into. The only thing I'm going to say is that the key idea that I have that I want to pursue is basically taking the exploded pieces that the optimizer has too much fun with and having a single opcode that goes all the way through to machine code as a pseudo instruction that encapsulates the entire dynamic bound check sequence. The key aspect here is that this gives us a single point on which we can hang the type, and it gives us a unique identity, a different SSA value that lets us check that separately from anything else the optimizer might combine it with. Okay, I'm going to skip regallic. Basically, we just do symbolic verification that the regallic result is equivalent, and we fuzz with this. The thing I'll say about it is that it's extremely effective, and we actually haven't had a regallic bug in production in 3 years because we do this fuzzing with symbolic checking. And then the last thing I'll talk about is inside the sandbox, right? So we've talked about sandbox security. We have formal verification, translation validation, great. Right, so that boundary is secure, but what about inside? And so, what is the threat model? Let's ask this question here. If we care about keeping our hosts safe, then that's all we need. But if we care about code attempting to subvert logic inside the guest, which we might if it's server-side WASM, for example, doing authorization checks, then we actually care about correctness of the language implementation inside the guest as well. And so we need a correct language implementation. One example of how this might come up is you have Cloud Bleed, which was a bug about 7 years ago. Cloudflare was leaking undefined memory from one connection to another, really, really bad. And so cross-request isolation is actually important, and we use the WASM boundary for that. We have separate sandboxes. But even within a single request, we might want correctness. And so how do we build correct JavaScript? Step 1 is use someone else's JavaScript. And so I'm talking about JavaScript as a guest here, but the same ideas would be applicable to other languages as well. So we started with SpiderMonkey, which is the JavaScript runtime produced for Firefox. It's fuzzed, it's got a security team, it's quite good. And then step 2 is avoid the JIT compiler. Because most of the CVEs that happen in language runtimes happen inside of JIT compiled code with things like type confusion bugs. Don't you want performance? Yes, we'll get there. Right, so, and that's all we can run on WASM today anyway. So basically, we can only compile an interpreter to WASM. We don't have a JIT backend for WASM. And so sort of the thing I want to say about interpreters is that interpreters are really easy to write and really easy to get right as compared to JITs. This should be uncontroversial, I think. JITs are an order of magnitude more complicated. You're sort of working indirectly rather than directly. The other nice thing about an interpreter is that it's portable. So if I'm developing on WASM, I have a much worse environment still today than I do on native. One tool that I really like to use is RR, the reversible debugger. It's fantastic for finding bugs. It only works on native Intel and some ARM chips, right? So on native x86, I have R, perf, GDB, Valgrind, all the things. WASM time GDB kind of works, but like kind of not, and I often get assertion failures. So I'd rather develop my interpreter natively and then just compile it for WASM. So the thing that we did, and I will go very fast here because I have 0 minutes left, is that we have a single source of truth, an interpreter, and we do partial evaluation to produce a compiler from that interpreter. You can see another talk that I've given to see how this works. And we get 2 to 3x speedups. This is real. It's deployed. And the thing that's nice about this is that we're developing a JIT from first principles, right? So basically the idea is that we want to have the semantics only in the interpreter, and then we want to have validated tools that give us the JIT compiler for free from that. And we have some ideas on how to do other optimizations. But yeah, limited formal methods can work. Meta compilers can work. And I think there's a lot more to do here. And WASM has set an excellent precedent with explicit semantics. That's all I had to say. So thank you, and any questions? DP? Yeah.
Just very quickly, as we're having questions, could we have the next speaker just set up if you move your mic? Okay, I'll check in with it.
Any other questions?
I have maybe 3 questions, and I'll
Okay.
go through them really quickly.
Yeah.
When you had a spec boundary, what are all the features you're testing in that spec boundary? Because we've had a few CVEs, but they're all in this overflowing stacks or type confusion, that sort of space. And I was wondering if you expect them or how you're thinking about them.
Yeah, so at the machine code level, but at the virtual register machine code level, pre-regallic. So there's a separate regallic thing that we do. There's still potential for still potential for issues in the glue. So that's why we have the end-to-end validation as well. Yeah.
Okay, and I don't know if you mentioned quite a bit about just bounce checking and like memory safety, but maybe control flow. Could you speak a little bit more in terms of control flow and how you're validating that that's safe?
So the short answer is that crane lift is not smart with control flow. Basic blocks remain basic blocks. We don't have any optimizations that change that. So we haven't put a lot of effort into that. If and when we do, then I'll have to think more.
I'll find you later.
Okay, thanks.
Yeah, so you mentioned quickly that you also add some code to protect against speculative side channel attacks.
Yeah.
Is that a worry for you? And would you also like to verify some of that?
It is a worry. So we do very basic mitigations. We do C moves rather than branches, which protects Spectre v1, not other variants, right? I think more would be nice. So yeah, I'd be happy to talk offline if you have more ideas.
Thanks.
We have time for a couple more questions.
Yeah, maybe this is too much in the woods, but I was a bit oh no, we don't have the slides anymore. This will be hard. I was a bit confused by what you showed, the logic that you showed when you did this addition on the pointers that there was a pointer to a particular thing at offset 0.
Yep.
And then you added an arbitrary number to it. Because the type had some assumptions itself about a certain thing inside its offset. Like at offset 80, there's another pointer or something. If I offset my pointer by a bunch, that doesn't translate. Right, like I have something at offset 0 that has at offset 0 plus 80 the right thing. Now I add 100 to it. Now at 100 plus 80, how do I know I have that thing still?
So the semantics are that the memory. So the fact on the pointer says that I am pointing to this type at this offset, and so if I'm at this type at this offset 80, for example, and I do a load with additional load offset 0, then I know that I'm accessing the field at offset 80. So we don't translate the type. The type is always a fixed layout with fixed offsets. We track the offset of the pointer within that type, if that makes sense.
So I mean, maybe you just couldn't see it because it was hidden behind the table, but the fact that you had on the added up pointer did no longer have the empty 0, or did it still have the empty 0?
So I think the example I showed never actually added anything to the VM context pointer. We loaded from it, and we got another pointer. And that pointer was another type that described the memory that it's pointing to. I can find you offline. And we can
Yeah,
go
I
over
guess
if
that
you
was
want.
a bit too fast for me then. Okay, thanks.
Yeah.
All right, thanks again
Thanks.
to Chris. Right, so now we have our next speaker, Byung-ji Kang, who is a PhD student at Carnegie Mellon.
Thank you for the introduction. I'm Byung-ji, and I'm a PhD student at Carnegie Mellon, and today I'm going to talk about my ongoing research on MLIR dialect for WebAssembly, which is a joint work with my collaborators Harsh, Brandon, and my advisor Limin. So to give you some background, we have been working on a pipeline to compile and deploy programs on multiple platforms. The source program could be some machine learning application or some general program written in a high-level language, and the target platform could be, So the target platform could be a web browser, desktop computer, or microcontrollers, and etc. And we know that WebAssembly is a great fit for this use case. It offers us several benefits, and importantly, it offers us great portability for our use case. So once we compile high-level programs into WASM, we can deploy them anywhere. And among those target platforms, we are particularly interested in microcontrollers for now because they impose interesting challenges. So different microcontrollers have different memory requirements and different hardware abstractions and resource constraints. So programming on microcontrollers means that we have to deal with low-level details of microcontroller, and this is very difficult to do correctly and efficiently if you don't have the expertise. But thankfully, WASM can be a good solution for this. It offers us the abstraction to decouple device-specific details from WASM code. This means that if we have a good WASM runtime, for example, WASM micro runtime for microcontrollers that is built by expert on microcontrollers, then we can just let the runtime do all device-specific details or optimizations, and the application developers can just focus on compiling their code into WASM without thinking about the underlying architecture. And also, we want to mention that high-level WASM features provide even more opportunities in this case. For example, suppose that we have a WASM garbage collection feature. We can use these to abstract away details of memory allocation strategies from usual level code to runtime implementation. So even if we have the same WASM code, we can use like different memory allocation strategies in different microcontrollers based on the memory sizes in devices and etc. Now the problem is that we want to compile these high-level programs into WASM. So the program could be a machine learning application or some microcontroller-specific application written in some high-level domain-specific language, or it could be some general program. And our goal would be to compile this into WebAssembly. So we need to build a compiler in some sense. And because we don't want to build a new compiler from scratch, we wanted to use a reusable compiler infrastructure like LLVM. And after that, we decided to use MLIR compiler infrastructure for our use case. It's a recently developed framework that is maintained by the LLVM community. It offers great modularity and extensibility. So let me briefly explain how MLIR works. So this is an example, simplified figure showing that how high-level ML program can be compiled into WebAssembly. So each box in the diagram is called a dialect, which is an abstraction layer in MLIR. It is a collection of operations and types that could be used to represent some concept. And MLIR program has operations in one or more dialects. And the compilation is done by a series of dialect conversion passes, which is shown as arrows here, which converts high-level dialects into lower-level dialects progressively. So for example, there is a TOSA dialect, which stands for Tensor Operator Set Architecture, and it has operations like toss out that constant, which defines constant tensor and convolution, applying convolution operation on them. And after a series of dialect conversion passes, we can actually convert this into lower level dialect, which is linear dialect. It has operations like matrix multiplication and etc. And for after applying more dialect conversion passes, we can actually convert this into, for example, SCF and ARIS dialect, where SCF stands for structured control flow, and it has operations like for loops. And ARIS is a dialect for arithmetic operations like multiplication and addition on scalar. And we can even convert this into CF dialect, which is unstructured control flow, which has operations like branch to label and etc. And after we get into this low-level MLIR dialect, we can finally convert them into LVMIR and use existing LLVM backend to convert this into WebAssembly. So this seems good so far, but there is one problem. The problem is that existing compiler infrastructures, including MLIR and LLVM, they choose to convert the high-level programming into some shared abstraction, for example, LVMIR, to make their compiler reusable. And this shared abstraction are often designed with conventional assembly targets, like conventional compilation targets like x86 and ARM in mind. So they have abstraction level that is similar or slightly higher than them. So this works perfectly fine for them, but there is a problem when it comes to WebAssembly. WebAssembly has features that are higher level than conventional assembly formats. So for example, it has instructions to define garbage collected data types and structs, and it can have like multiple memory spaces, and even like the stack switching feature will provide us a way to define continuations and switch between them as WASM instruction level. So while these kind of features may have existed in the high-level program, the existing compiler infrastructures actually de-abstract this concept into some shared abstraction. And from that shared abstraction, it is difficult to take advantage of these high-level WASM features and use them effectively. So the problem statement can be summarized into one sentence. Existing compiler infrastructures do not support compiling to WASM with high-level features in a reusable and extensible way. So in this talk, we will propose a new MLIR-based compilation pipeline that solves this problem. So this is the outline of the remaining of the talk, and I will start with a motivating example first. So first, as a motivating example, I will explain about the intermittent computing, which is an important class of application in microcontroller programming. So the goal here is to run programs on small microcontrollers that doesn't have any battery or power cord. So how these devices work is that they accumulate energy from external environment, for example, from sunlight, and store the energy into some capacitor. And once enough energy is accumulated, it goes through execution phase, which lasts typically for a few milliseconds, and the program runs for that time. And after that, the energy runs out, and the microcontroller experiences power failure, and we go through charging and execution phase again and again. The problem here is that when it experiences power failure, the microcontroller loses all its volatile state. So we have to find a way to make sure that the program state is not corrupted. Program state, which consists of both non-volatile and volatile memory states, is not corrupted during frequent power failures. And there are several researches that have been done to overcome this issue, and I'm going to introduce one, which is called Alpaca programming model. This is a programming model for microcontrollers for intermittent computing, which uses some concept of task and transition between tasks. So you can think task as a granularity of atomic execution, and transition to statement as a operation that saves some context and switches to another task. We have also built a domain-specific language for this intermittent computing with some task and transition to operations. So now the problem is that we want to compile this into WebAssembly. And ideally, this transition to statement should be compiled to some form of context switching. But the problem is that context switching on microcontrollers is very difficult to implement well. We may have to think about whether to enable or disable certain interrupts and traps during context switching. And we also have to think about whether to store the switched out context in certain memory regions, because like different regions of memory, different memory regions in microcontrollers have different like access latency. So we have to optimize this somehow. So this is very microcontroller specific thing and difficult to implement, but there is one solution that we can think of, which is using a stack switching proposal. This proposal provides instructions to define and define continuations and switches between them. And I think like this will be covered later in this workshop. But from our perspective, this is great because we can use this to abstract away details of context switching from WASM code. So the runtime implementation which can be done by each microcontroller experts, can take advantage of like this microcontroller specific optimizations during context switching. And also there are more high-level WASM features that could be helpful to abstract away device-specific details from WASM code. For example, there could be multiple memories, garbage collection, exception handling, and etc. And more importantly, there will be more of such features in the future, as WASM is an evolving language, unlike other hardware-level assembly formats. Now I'm going to talk about problems with existing compilers, or why it is difficult to generate such high-level WASM features from existing compilers. First, there are compilers, some languages like Golang and Haskell chooses to build their own compilation pipeline for WebAssembly and other assembly formats. This approach is definitely flexible, but this is not reusable. We need duplicate work for each source and target language. And also there is one WASM-specific complexity, which is that WASM itself is evolving. So if we build a custom compiler, the developer is responsible for updating the compiler by themselves as the WASM features are being added. And also, next let's talk about the reusable compiler infrastructures. So the most popular reusable compiler infrastructure is LLVM, which is used by C, C++, and Rust. But as it goes through a shared abstraction layer called LLVM-IR, it experiences abstraction loss, as we explained earlier. Then, what can we do about this? The first option could be re-abstract high-level concepts from low-level abstraction. And this is actually an attempt that is done by Amscripten, which is LLVM to WASM compiler. Since WASM, unlike LLVM, which allows arbitrary form of jumps to labels, WASM only supports some certain form of structured labels for security and simplicity reasons. And because of that, the Amscripten developers had to build a control flow transformation passes to convert control flows in LLVM-IR into WebAssembly compatible ones. They did it through a non-trivial algorithm called relooper, but in general, there's no guarantee that such kind of re-abstraction is doable. In general, re-abstraction is hard. And another thing that we can think of is to extend LLVM-IR to preserve the high-level information through the compilation pipeline. But this is also difficult because LLVM-IR is not meant to be extended in some sense. It offers some form of extensibility, but in general, adding a new instruction or adding a new type will bring compatibility issues to LLVM, and it is difficult to use this update LLVM frequently to keep up to date with WASM changes. Then, how about existing MLIR to WASM pipelines? So as I mentioned earlier, MLIR has multiple levels of abstraction, and it is designed to be easily extensible, so it has some advantages over LLVM. But fundamentally, we still lose abstraction in this pipeline because what we are doing here is to compiling the LLVM MLIR dialects into LLVM-IR and rely on LLVM backend to generate WASM. So our idea is to get rid of this LLVM-IR from the compilation pipeline and keep the abstraction as much as we want. So let's get back to this diagram showing the example of compilation pipeline from high-level ML applications to WebAssembly. What we do here is, instead of using LLVM-IR, we introduce a new dialect in MLIR world called MLIR WASM dialect. This dialect has a one-to-one correspondence with WebAssembly, so it can be directly translated into WASM. So now the compilation to WASM can be done through dialect conversion passes that converts existing MLIR dialects into the WASM dialect. So for example, we can build dialect conversion passes from low-level memref and RS dialect into WASM dialect, which is straightforward. And another benefit is that we can choose which dialect we want to convert from. So for example, instead of generating like WASM dialect from CF or unstructured control flow dialect, we can actually generate WASM from SCF, structured control flow dialect. So the advantage of doing this is that in this case, this translation is trivial, almost trivial. We don't need to think about re-abstraction algorithm like relooper as LLVM did. And another benefit is like, let me talk about an example of tensor and memref dialect first. So tensor dialect here is a dialect for high-level immutable data type for tensors, and memref and we can actually convert this into lower-level dialect, which is memref dialect, and it has operations related to memory allocation, access, free deallocation, and etc. What we're doing previously was to convert this memref dialect into LLVMIR and to WebAssembly. But actually, we can actually think of converting tensor dialect directly into WASM dialect. For example, using WASM GC features, using the arrays, types, and structs type that are provided by WASM. In this sense, we can take advantage of high-level WASM features. And for example, if you have a high-level language, if you have implemented a high-level language, what you can do to compile this MLR into a, you can actually compile this into MLR or WASM dialect before like losing its abstraction. So in that case, we can use high-level features of WASM. So I'll give you a case study, intermittent computing language as an example. So we have built a domain-specific language for intermittent computing, and in order to compile this through MLIR pipeline, we have developed an MLIR dialect that mirrors this domain-specific language. So our goal is to compile this into WebAssembly. And actually, this is doable, even without WASM dialect. But without WASM dialect, what we can do is to convert them into LLVMIR with complex coroutine-related intrinsics and rely on complex compiler transformation passes that inserts the context switching code to user level. So for example, we have to include malloc, which is responsible for allocating frame to store the context, and we have to do store and save and restore context at user code level. So in that case, the binary size will be bigger, and we cannot take advantage of any device-specific optimizations. However, if you go through WASM dialect, the transition to statement can be actually simply converted into single switch statement in the stack switching proposal, which performs some kind of context switching. And through this, we can actually get smaller binary size, and we can also have to bundle the malloc code for this. And also we have room for more optimizations. We can rely on runtime implementation optimizations that utilize the domain-specific information, device-specific information. And also I want to mention that once we build a dialect conversion path from some dialect to WASM, we can actually, all the high-level languages and dialects can reuse these conversion paths. So this is a reusable compilation pipeline. And now I'm going to briefly mention our ongoing work on performance evaluation. So as we haven't implemented any optimization on our compilation pipeline yet, this is obviously much more slower, which is expected. But actually, for our use case, we are focusing on compiling WebAssembly ahead of time to binary machine code and also apply binary optimization before that. And in this case, it turns out the performance is quite comparable. There are some points where the performance of my compiler, where the code produced by my compiler is somewhat slower than LLVM, but there are also cases where my compiler actually produces faster code, which is interesting result, considering that I haven't implemented any optimization in my compilation pipeline yet. We are still figuring out what is exactly happening here.
Can you speak to a little bit more of what's in your benchmarks? Just by the names, they seem like they're doing more long and cheaters, vector operations.
Yeah, so it's mainly related. It's actually a benchmark suite for polyhedral optimization, for testing polyhedral optimizations, and I chose this because it has MLIR port of it, and it mainly has like benchmark suite related to like matrix multiplication and dealing with arrays and etc. So it is mainly for like tensor operations, and we have tested this on microcontrollers. So I'm going to finish the talk with possible future works. So first, I think I can use this MLI WASM dialect to support other WASM features. For example, early phase WASM features that don't have much users yet. I think we can use this MLI WASM dialect to create or get more users or high-level languages that compiles to them. And also, as we don't use LLVM anymore, I think this is a great opportunity to perform end-to-end compiler verification or analysis research. So because LLVM is a so large project, it works as some kind of black box for if you want to perform some end-to-end verification. But as the compilation pipeline is now much simpler and can be customized more easily, I think we can also do research on this direction as well. So this is all of our talk, and I'm happy to take any questions.
Thanks, that's great. Just before I open it up to the floor, I have a couple of questions. Since Sam is in the room, I won't ask the stack switching question. But I was interested, I didn't realize MLIR had so many different dialects. Did you ever find that there was some tension in designing the WASM dialect between reusing the existing dialects, so you're not having to come up with a lot of your code, and at the same time, adding all these WebAssembly specific things? Were there any design decisions you might want to revisit or iterate on later?
I think there actually are a lot of things. So first, like WASM is a stack-based assembly format, while like MLR is originally a assembly originally format for SSA forms, which has like variable declarations and etc. So we have to handle that conflicts in that somehow. And also, WASM has some operations like block, so if you branch to a block, it branches to the end of the block, but not the beginning of that. And like MLIR doesn't have like such notion of control flow, so it also has some issues there. So we need to fix that. And also we are going to refactor our pipeline to have add more like intermediate dialects, but that's, yeah.
That's very gratifying to see you making use of the stack switching extension. I'm curious, have you actually tried running that code? Because there's only really an experimental implementation so far in WASM time. Have you?
So yes, we are trying to running it on WASM-FX time. Are you a developer of that?
He's the main proposer.
Oh, it is.
I'm the champion of the proposal.
Actually,
one of the co-champions.
I remember that I've created a GitHub issue on the WASM-FX time that like I needed some stack switching feature.
Ah, right.
Yeah, that's like what we were looking for.
Oh, cool. So you've actually tried running the benchmarks.
And we are also trying to running that on microcontrollers by porting them on WAMR runtime.
Excellent. Great.
You two should definitely talk to each other.
Yeah, sure.
Hi, so this is more of a clarifying question, I suppose. Like, you did not only define a WASM MLIR dialect, you also wrote a compiler from the WASM MLIR dialect straight to WASM. And you're skipping like the LLVM part entirely?
Yes, I'm skipping that entirely. And the goal of designing the WASM dialect, the design decision of like making the WASM dialect is to make it as similar as the WASM itself. So the translation from the MLI WASM dialect to WASM can be done trivially, just by the one-to-one translation.
Okay, thank you.
I'm curious what microcontrollers you're running, just in terms of, especially because I know that a lot of microcontroller programming happens in C, and LLVMIR should be able to deal with that fairly well.
For now, we are running it on Apollo 4 device, which has like Cortex-M4 CPU.
Okay. The other question was, are there any WASM to WASM optimizations that MLIR can do better than maybe binarian or the current LLVMIR in your experience?
I think there could be, because like, but I don't have a clear answer for that. We're still looking into the issue. Maybe I think like by looking into this performance, oh, sorry, I don't have like the slides, but by looking into the performance gap in our benchmarks, I think we can try figure it out. Yeah.
So for our final talk of this session, we have Andrew Brown. Andrew is both an engineer at Intel, and he is also on the technical steering committee of the Bytecode Alliance. And in this context, he's also a PhD student, so wearing a lot of different hats. So take it away, Andrew.
All right. Let me get my clock. 20 minutes, right? All right, cool. Good morning. My name is Andrew. I'm here with Andrew Tolmack in the back, trying to present a talk on meta tracing for WebAssembly. So our approach is to build a set of distinct tools that will use trace-based optimization to improve interpreter performance in WebAssembly. And we're interested in feedback on whether our tools are useful elsewhere, or specific details of our design. Okay, can I get this a little higher? Is that better? Good. So we start from the following scenario. Developers write programs in a high-level interpreted language, and the interpreter is compiled to WebAssembly. Then we have many users which invoke each program many times, and for each invocation, the input is dynamic. You might see the 0, the 1, the 2, the 7, but we know that the program and interpreter pair is static. And WebAssembly hosts like function as a service or distributed compute hosts of various kinds will run these invocations in a WebAssembly engine. And the problem is that interpreting these programs is slow in an interpreter compiled to WebAssembly. And so we're attempting to solve this with our design. And one thing to note is that this particular scenario enables us to do things offline because there's multiple invocations of the program. So we'll argue that this problem matters because there are already various attempts to solve this. So there's the just-in-time compiler approach, and for our scenario, this would look like finding hot functions with while an interpreter is executing, compiling the program's bytecode to WebAssembly, and then somehow patching that new WebAssembly into a running WebAssembly instance somehow. So Dimitri from Megalia has demonstrated this approach last year at WASM.io, and this is a very natural, common sense approach, but not all interpreters have it yet. The WebAssembly spec has no standard way to patch JIT compiled code into an instance, and as Chris kind of mentioned earlier, this approach is too risky for some hosts, and so that led to a second approach, which is the partial evaluation approach that Chris described earlier. Briefly, kind of 3/4 through the talk, he talked about Weevil. And so in our scenario, to describe his approach, a tool would combine the interpreter and the program bytecode, both which are static, to specialize the interpreter for that program using partial evaluation. And Chris and Max built Weevil to do just this for interpreters that are compiled to WebAssembly. So this is a well-studied approach, been taken by Graal and Truffle previously, but it is complex. It does require minimal source code changes to the interpreter, which we're trying to avoid, and it's naturally limited to the information that you have statically. So you know the program bytecode, you know the interpreter code. That's all you know at the time. And so our approach is distinct in a few ways. So our direction is trace-based optimization. And so specifically, you know, the approach we're taking here is called meta-tracing. And I'll explain that in more detail later. But you know, the general idea is we collect traces of WebAssembly programs, and then we create optimized fragments from those traces, from the hot regions within those traces. And then we insert these optimized fragments into a new optimized program, and then we run that optimized program later. Our reasons for choosing this approach is that no JIT is needed, and so all kinds of interpreters can benefit from this approach. We can build, you know, distinct reusable tools for each phase in our infrastructure, and those might be useful elsewhere. And we kind of believe these offline WebAssembly to WebAssembly transformations are simpler and perhaps faster because, you know, when you do this stuff online, you have to make up for the runtime overhead of tracing and optimizing as the program is executing. We don't have to do that in our offline scenario. So the big question for us is, will the trace-based approach that we're trying improve interpreter speed? And I just want to point out that, you know, there's a history of trace-based optimization, but just, you know, the differences with our approach is that we should be able to take any user language as our trace, you know, for tracing, and that we're doing this offline instead of online. So let me walk through an example to describe how meta-tracing might work. So what we have here is a Java program that on the right has been compiled to Java bytecode. Now, of course, one might want to compile Java directly to WebAssembly, but for, you know, our research prototype, we're not doing that. We're just going to keep this bytecode separate. And so you'll notice that this Java program has a loop, and we'll call this loop the user loop. So the body of this user loop, that's the bytecode on the right. And then the Java interpreter, we're going to interpret this bytecode. That's written in C, and it has a loop which we'll call the dispatch loop. And so this retrieves the bytecode and, like, you know, implements the bytecode. And so 2 observations here. Most of the execution time is spent in this user loop, or due to this user loop. And secondly, when we're interpreting this Java bytecode, you know, everything related to the dispatch loop has overhead. And so what does meta-tracing do to improve this? Well, let's just focus in on 3 of the opcodes inside that loop, the load, the add, and the store. And I sort of split out the interpreter part of this into a control flow graph, kind of simplify. And so if we trace our execution, the execution of these opcodes, you'll see that we spend some time doing dispatch stuff. Then we do the user load. You know, not all the instructions are shown for brevity, but then we come back to the top of the dispatch loop, and we do that again, and we do that again. And you'll see in green that that's the user loop parts of this. And what meta-tracing does is it finds those, and it extracts those things into an optimized fragment, getting rid of the dispatch loop overhead. So, you know, 2 intuitions here. One, if we can avoid that dispatch overhead for the user loops, we can improve performance, right? But we need to assume that the bytecode is not changing under our feet. And secondly, once we get the implementation into this optimized fragment, an optimizer can do a better job, or there's more optimizations available to improve performance. But what do we do about this asterisk? You know, guards for off-trace exits. What about, for example, this opcode, compare greater than or equals to? You can see the implementation in C for that opcode. And in our trace, we'll get you know, events that look like this. We'll get an event that is related directly to the dispatch loop, which is, you know, operating on the bytecode itself. But then we'll also get events that are related to the actual implementation of the opcode. For example, if we're greater than or equals to whatever number, we need to do this versus that. so if a guard fails, so we need to maintain this logic. This unknown control flow needs to be retained in our optimized fragment so that our optimized fragment is still correct. And we do that by the means of guards. So our optimized fragment will include guards that if the guard fails during the execution of the fragment, we have what we call an off-trace exit. So we're leaving the assumed path of the hot loop, and we must de-optimize to the original interpreter. Typically, how that's been done in the past is we reset all the original interpreter state, and we go to that location in the original interpreter. But even though that's a known problem for meta tracing and kind of solved, how do we do that in WebAssembly? There is no go-to in WebAssembly. The structured control paradigm of WebAssembly prevents that. And so I've given you sort of a broad overview of what meta tracing is, what the problems are going to be, and now let me dive into our design, and I'll dive specifically into two topics here, finding loops and how we're going to de-optimize these off-trace exits. And so, a general overview of our architecture is that first we will instrument the WebAssembly program, which is an interpreter, to capture traces, one or more traces. Then offline, we'll use that trace to find loops and optimize the loops into these optimized fragments and somehow reinsert them back into the this WebAssembly program. And so then subsequent invocations of the interpreter will use this optimized version, which has been specialized to the program. And when we get to an off-trace exit, we'll de-optimize somehow. So we'll talk about that later. And the green check marks here mean that we have working prototypes for some of the phases. Our primary data structure in that design is the trace. And so that's a list of events that can recreate an execution. A trace could be saved to a file, but size and collecting the trace, those are limiting factors here. So our current approach is to just instrument a WebAssembly file with WebAssembly host calls. And this is naive, and we know it'll slow down execution, but we know that there are future mitigations that may resolve this, like reducing the number of events or using special hardware. I won't talk about that here. Our main goal for these traces is to use them to do meta tracing. So, find those user loops and make those optimized fragments. But there are other things that the trace could be useful for, like creating macro ops or for branch hints, which we can talk about later. So let me dive, more deep into how we're going to find these user loops. So what you see here on the left is a trace, and the trace events describe what happens, what are the branch decisions at these BR table instructions. What we then do is we apply an algorithm, a string algorithm taken from DNA sequencing analysis to find tandem repeats. So these are repeated subsequences within a trace. So, but when we get those tandem repeats, is this truly a user loop? So you'll notice that the values for this instruction, 29, 27, 162, those are byte
So I was wondering when you mentioned like finding the PC, that technique seemed like it was specific to a WebAssembly interpreter interpreting another interpreter, which is a Java interpreter in this example, which is then interpreting a user loop. I mean, is there a way of, I don't know, phrasing this in a way which doesn't imply that the function that you're because, I mean, originally we're talking about like arbitrary functions where you know the function, but it's not, that function might not be an interpreter. Is there a way of phrasing this which, you know, isn't so tied to being interpreter specifically?
Yes, I think it could be. So specifically, you know, it's important that we have a specific use case to target, and it's known that interpreters can be improved via meta tracing. So we need to at least hit that. But I'm hopeful that tracing would be able to find other opportunities that are not specifically interpretation, where the same kind of pattern happens, right? Like the data has a specific, you know, essentially a user loop that a trace can extract, and then we can generate an optimized fragment for.
Hi. So is this approach like tailor-made for specific interpreters? How difficult would it be to use it for a new kind of interpreter for a different language, something like that?
So the idea is you compile your interpreter to WebAssembly. So as long as you can compile your interpreter to WebAssembly, then the next decision is if we can automatically find the PC, good, perfect, no work needed, right? You just have to compile the WebAssembly. If we can't find the program counter automatically, then we may need to ask the interpreter author to add an annotation, say, hey, here's our PC. But that should be it.
I'm not sure if I understood it fully, but the block lifting translation you showed looked a bit like a CPS translation. Is that?
Yes, that's correct. It is
right?
Very similar. Yeah, go ahead.
So that might suggest that stack switching could be another alternative.
True. Yeah, I've looked into that a bit. I still have to fit all the pieces together, whether that is in fact the case. We had hoped to use stack switching perhaps as a ancillary, you know, to help with that switch. But yeah, I'd be interested to talk more to see what you think.
I mean, it'd be interesting to see what the performance cost would be as well.
Yeah, that's a big unknown here.
Yeah.
So.
When you were looking at kind of existing previous works, did you find any people who'd already experimented with partial evaluation for WASM in different ways, or are you kind of the blank slate here?
Well, we're kind of doing the trace space approach versus partial evaluation. Chris already has the partial evaluation locked down, so. But I've not heard of anyone else doing tracing in WebAssembly specifically.
Okay, thank you. Let's thank Andrew one last time.
Thank you.
Okay, so now we have a half-hour break. Thank you all for coming to this first session. Tea and coffee is only on floor 3. Oh, was it changed again? Okay, we do not know where tea and coffee is. The best guess is it's on floor 3, which is one floor up. If that's incorrect, I'm sorry, I take all the blame. But back here at 11. welcome back to the second session of the WebAssembly workshop. We had originally timetabled Dayan Stefan as our invited speaker. Unfortunately, at the last minute, he was not able to make it. But I'm very, very grateful and happy to be introducing Shravan Narayan, who is an assistant professor at UT Austin, who flew with less than a day's notice here to give this talk. So a big hand to Shravan.
Thank you.
And please take it away. I see your screen is not displaying yet.
There we
Perfect.
go. Awesome. All right, so hello everyone. I'm Shravan. I'm subbing in. Oh, I should be here. Hello everyone. I'm Shravan. I'm subbing in for Dayan today. And I should kind of start by saying a lot of the stuff I'm going to talk about is the collaborative work of a ton of people. I'm just here telling you about it. And I know a bunch of people in the room might have wanted to hear from Dayan, but no worries. I'm well set up to fill you in on all the stuff that we've been up to as a group. And in fact, I started these slides 7:30 p.m. yesterday, which is a full 12 hours before Dayan would have started the same talk. So we should be fine. We should be fine. So I actually have met a few of you in this room. For those who I haven't, let me just tell you very quickly who I am. I'm an assistant professor at UT Austin. I actually did my PhD at UC San Diego working with Dayan. And the stuff I'm going to tell you about is research that I've been kind of involved in for the last 8 years at this point, which feels like quite a while. And I'm going to start this talk at the beginning, just so that I'm kind of making sure everyone follows along. I know a couple of you may have seen versions of this talk. So what I'm going to do is also explicitly mention all the new stuff I put in when that comes up. So feel free to let your mind wander if you've seen some of the bits before. Okay, so let's start at the top. Why are we worried about, or what are our interests with WebAssembly, right? And so it starts with something that looks like this, which is software suddenly realizing, oh, there's a 0 day in the wild, we need to go patch this. And this happens with browsers, for example, all the time. And these are not simple bugs. They are sophisticated attack campaigns with like a chain of bugs starting with memory safety, privilege escalation, platform-specific stuff, and so on. Now, if you zoom into just the core bug in this big attack campaign, you're going to actually see that it's a CVE in this library called FreeType, which is a font rendering library used by Chrome. Not written by Google, but used by them. So it is a third-party library. And this actually means that Chrome had a 0 day because of code they didn't even write. And this sort of thing is super common. It happens again and again. And don't take that 2020 example like as the only case of that. I can literally give you one from last month if you want, right? And these sort of memory safety bugs simply aren't going to go away no matter how much we wish for it. 70% of all memory safety bugs or like long-term studies in browsers and OS are these sort of, 70% of bugs are these memory safety bugs. And now the obvious way we would like to tackle this is to, start doing things a little safer, maybe rewrite things in Rust. Now, as a practical matter, there's a lot of code out there, a lot of C, a lot of C++. It's hard to rewrite that overnight. It's hard to rewrite that over the next decade. It's hard to rewrite that over the next few decades, if I'm honest. The other thing we can kind of do is to split apart all our applications into privilege-separated kind of designs, which is make them a bunch of processes, separate out the code, and that way each process can't affect each other. Now, browsers are doing this pretty extensively already, and we're hitting a ceiling when it comes to performance of that style of doing things. And all of this is like discussed in detail in various talks given by a lot of folks, actually. So when we looked at this, we wanted a different way to tackle this, and so we started with this thing called in-process sandboxing, which in short was, let's take all the third-party libraries or even first-party libraries in Firefox and start putting them in WebAssembly sandboxes. So we're no longer wanting to build an application like a monolith where a memory safety bug in one component affects the world. Let's kind of keep things contained. And so, and we did actually. It did actually happen. It took quite a while. So I'm going to start by telling you how we actually made all of that happen. And here's roughly what I'm going to try to cover in this talk. We'll start with talking a little bit about how we made WebAssembly workable for this library isolation kind of use case. And I'll talk about all the stuff we've been doing over this, I want to say, 6-7 year project, including stuff that's just happened last week. After that, we'll talk a little bit about the security of WebAssembly and the sort of work we've been involved in. Chris has actually talked to you about that extensively, so I'm not going to spend a lot of time on it. I just want to kind of show you how it all fits into the overall picture. And finally, we're going to talk about performance. We're going to talk about performance a lot, actually. So we're going to tell you about 3 different ideas we've had to speed up WebAssembly. And then, if time permits, and I really hope it does, that's the cool stuff at the bottom, the ongoing work that literally no one has seen. It's on my computer and nowhere else. Okay. All right, so let's just jump right in. Start with process sandboxing. All right, in an ideal world, I would just be able to do this. I take Firefox, compile the libraries to WebAssembly, and I'm done. And this is my little approximation of a WebAssembly compiler, which is to insert bounce checks before every memory access. We all know it's a little more complicated than that, but that's good enough for now. Now, if I could just recompile these libraries and then use it, that should kind of be enough, hopefully. In reality, that's not quite the case. Because when you do this, firstly, you need to figure out how to really decouple the library. Not just move the code out, but deal with all the shared data structures. And then you need to restart sharing just the data structures that make sense to share, that are actually used by both the host and the library. And you might not want to copy data too aggressively back and forth, or you'll wreck your performance. And what's more, you have to insert a bunch of security checks, because the library could corrupt the data structure and you could end up using it. So if you don't check it, all of the security you get from WebAssembly is gone in this use case. So by the time you actually do this, it becomes quite tedious. So let me show you a super simple example. This is the code for an application that renders JPEG images. It's super tiny. I've tried to fit it into one slide as possible. Don't worry about reading it, right? Like it's an application that renders JPEGs. If I were to make all of those changes I just showed you on the last slide to actually integrate a WASM sandbox libjpeg in an application, that's what the code looks like. Again, don't read so much into it. Just, for example, look at the middle line. Just look at the number of checks and ABI conversions and marshalling that has to happen. I don't know what that line says anymore, and I wrote it. So this is clearly not going to work in practice. And even if you somehow succeed in doing this for one library, that's an incomplete picture of the libraries in a browser, of the third-party libraries in a browser. I think the actual image extends about 3 times the size of this projection screen. So we're not going to get away by doing this slowly. And we're not the only ones to kind of come to this conclusion. There are other folks as well, folks at Google who've tried this. And the conclusion is it's pretty much impossible to do this by hand. There's just too much interleaving. There's just too many changes required. So this is where we started this work called RLBox. It's a work we published at Usenix Security 2020. And the idea was to use a type-based approach to sandboxing, where types can hide all of this mess. We can hide the low-level sandboxing details, deal with the ABI conversions automatically. And by API conversions, I think this room probably knows what I mean. WebAssembly, at least the memory 32, uses more or less 32-bit ABI conventions, 32-bit ints, 32-bit longs, so on. That may not be the same as your host. So you suddenly have to deal with all of that, and RLBox will do this for you automatically. It deals with data marshalling as much as it can automatically. It uses types to track untrusted data and control flow, and essentially give you kind of compile time errors if you didn't add a sanitizer to data that you should have sanitized. It also allows you to adopt these sort of security checks and make all those changes I showed you incrementally. You can literally do it line by line. You can change one line, compile the whole application, see that every test passes it, and deploy it. And in fact, when we did this in practice, we did do partial migrations and in fact deployed it. This did actually happen in production. And all of this is done with RLBox as a pure C++ library, which was the hardest part of this. And really, if you look at RLBox in its core, it just boils down to 3 principles, which is RLBox wants to be in charge of control flow in and out of the sandbox. So when you invoke a function in the sandbox, use its API, sandbox invoke. Next, every time you get any data from the sandbox, you should mark it as tainted. So in this example, when you read the size of an image parsed by the libjpeg, you've obviously got that from the sandbox libjpeg. So that is now a tainted uint32, not a uint32. And finally, when you use this tainted data in functions like memcopy, RLBox is going to force you to add a sanitizer there. Now, I should clarify, it can't tell you whether the sanitizer is right, but it's going to tell you you need to have something here. Okay, so hopefully we're all following so far. And I just want to show you the same libjpeg application example and what it looks like with RLBox and these 3 rules. So this is what it now looks like. There is a lot of yellow, but if you actually look at it, it's far more readable. It more or less, the original code stays as is, with a little bit of type annotations here and there. And this is kind of the thing that actually makes things practical for us. And why all this matters is, when we had this sort of framework to help with our library sandboxing, we could sandbox a library in a matter of days. Now, if you include testing and all of the things involved in real production deployments, let's call it a couple of weeks. Still very reasonable. And so we actually used this technique and deployed this in Firefox. And this was actually a very, very detailed and slow process, just because anything that touches production for millions of users, people want to be careful. So we actually did this research in 2018, 2019, tried a bunch of approaches to make this work. It didn't work. Finally, we decided to work with Lucet, which is, I want to say, a precursor to Wasm-Time. I don't know if that's the technically correct description, but it's a Wasm compiler. I think right now it's no longer supported and everyone uses Wasm-Time. But we started here, and we got this working in Mac and Linux for a single library, just one, sandboxed in Firefox, and it's running. And it took us the better part of 2 years to actually get more than this. And one of the key elements we had for our use case that was successful for us is moving to a different WebAssembly compiler, Wasm to C. And I'll talk a little bit about this. In this use case, it actually turns to work out pretty well. And with this move to Wasm to C, we were actually able to get every operating system that Firefox will run on supported. So this includes Linux, Mac, Windows, and Android. So literally on the phones. And we sandboxed a whole bunch of libraries, and this has all been running since then. And after that, we spent a bunch of time improving all of the infrastructure to kind of keep this all working well in place. And this has nothing to do with sandboxing, but just shows you a little of the extra pieces that are involved in making all this kind of work out in production, right? Like things like crash reporting, how quickly do you spin up sandboxes, when do you destruct them, how do you kind of keep things in sync with upstream code, et cetera? Because we forked Wasm to C for a longest time, and it was a bit of work to get all that merged back upstream. And something that happened in September 2023 is we started looking at a library that relied on SIMD. And WebAssembly SIMD is now well supported, which is great. We are a very, very grateful user of this feature. But we needed to get it to work in Wasm to C. And for those of you who don't know, Wasm to C is this interesting compiler that takes a WebAssembly file and converts it back to C. Not the original C that you started with, but C with, let's say, bounce checks, just for simplicity. So it's sandbox C. And effectively, when you think about it, Wasm to C plus GCC is a Wasm compiler, if you just put it in a box. And we needed to figure out how to support SIMD here. And the way we did this is to use this library called SIMD everywhere, which basically converts intrinsics to intrinsics. And so if you actually look at the round trip path of how we are compiling code now, it's to take a library which uses intrinsics, libpng for example, convert that to WebAssembly and use Wasm to C to, and Wasm to C SIMD support itself uses SIMD to convert the native intrinsics to Wasm intrinsics. Then we, I messed that up. Let me try that again. We take the libjpeg code, compiling with Clang to a Wasm file, using SIMD everywhere to convert the native written intrinsics into Wasm SIMD intrinsics. We take that file, compile it with Wasm to C, use SIMD everywhere again to convert the Wasm SIMD intrinsics to the native intrinsics, and compile this. And weirdly, this is all fast, or fast enough. Like it had no reason to be fast. It just was fast enough, and we shipped it. That performance of that library was 30% overhead or 40% overhead before, and I think it was down to 7% after that. And stuff that we've been doing since then, we've been trying to improve the RLBox framework. We have something called RLBox v2 in the works, and I'll show you just a couple of the problems it handles. And this other project that's ongoing, which I literally had to name this morning for this slide, which I'm going to call Sandbox Auto Sanitizer. So this is some of the new stuff, and I'm going to talk a little bit about that in a couple of slides. But first, let me tell you about the stuff all the stuff that's happened up to now. And there's going to be an obvious question when you look at this sort of timeline. Why so long? Well, cross-platform support is just painful. It is. And by the time you hit all the OSs, all the architectures, and we support more CPU architectures than that, by the way, we support all of them, and all the compilers, this is a mess. So for example, here's my description of one of the bugs I had to deal with. When using MinGW on the build servers in some OS, I don't remember what it was, thread local global variables of struct types failed to compile because of, and at this point, if your head hasn't exploded, I worry for you. This is painful. On the other hand, for those of you who are following all of that and are like, oh yeah, handle these bugs all day, please talk to me after. You sound like my next collaborator. All right. Beyond that, we had to work a lot to get WASM to see, fast, building efficiently, and so on. There's a bunch of fixes I won't talk about. But at the end of this is what we managed, which is 7% on XML parsing, 10% on font decompression for sandboxing these libraries in Firefox. The XML parsing is particularly interesting because that is a super hard path thing. And that is something that was really, really considered carefully before we sandboxed it, because Mozilla was wary that we would kind of destroy the performance. Because everything from SVG files and XML files on the internet are, go through that library. So this was kind of a big deal for us. And the thing that kind of made all this possible was WASM2C. WASM2C, and I kind of described the pipeline a bit earlier, but essentially what makes it useful for us is it's super simple to extend. So we can support extensions, in fact, support extra different ways to enforce things instead of just guard pages or just bounce checks, etc. And I'll talk a little bit about this later. We can even do interesting things like ensure the WASM2C outputted code works with ASAN. Very little work, actually. The only thing we kind of really need to add in is a little bit of like WASI support. We don't want to add all of WASI. Firefox doesn't need it. And we want to keep the TCP low. So we have a very minimum WASI that supports all of this. And literally all it lets you do is print or something and get the time, I think. And the nice bit is that C produced is now compiled with Clang and GCC, which is a compiler that's been optimized for decades. It's great. Like, we get good performance out of that. And so here's my kind of controversial question for you, or I don't know, just the interesting question, let's say. What is the fastest WASM compiler now? And yeah, no, generally shout it out. WASM2C plus GCC. Okay, I might have primed you badly here, which is my fault. Any other suggestions? WASM2C plus LLVM. Oh my God, okay. Really, no mentions of WASM time. Huh. Well, no, so here's the thing. WASM time 2 years ago was a slightly slower compiler because it was in development. WASM time is pretty damn fast right now. It is actually faster than these things. Like, despite half the things I tell you, it is still the fastest out there. With a caveat. The thing about WASM2C code that you spit out is that little bracket at the end. We get to do LTO, we get to do PGO, we get static linking in Firefox. That is another 15% in performance. So no matter how much work we put into the WASM compiler, sometimes things like that just tend to matter more. So this is an interesting observation for us. And anyway, kind of stepping back, what does this all mean? Well, if we look at the history of bugs in expat, that XML library I told you about, there's a lot of CVEs, a lot of memory safety bugs. And hopefully the goal is we don't have to worry about those anymore. And we had the opportunity to figure this out in practice. So this is a bug, I hope you can read that. This is a bug thread in Bugzilla Firefox. I'll read it out if you can't see it. Essentially, the first question is, lately, let me do this way. Lately, some expat CVEs popped up. The expat library is sandboxed in Firefox as a version 96 with ROBox. But the ESR, the extended service release, it doesn't seem to be covered. Can you investigate whether these vulnerabilities are relevant? Response from Bobby Hawley, who's now the CTO of Firefox. Oh, actually, looks like there's a lot of CVE, I'll paraphrase, there's a lot of CVE patches. It's just easier to uplift all of the RLBox sandboxing work for sandboxing expat, rather than the individual CVE patches. So that actually is what ended up happening. And which is kind of this very weird takeaway, which is apparently sometimes like it's cheaper to kind of like even just sandbox it than to sit and fix all the memory safety bugs you have in your libraries. And so hopefully the point of all this was to ensure the CVEs in third-party libraries do not translate to CVEs in Firefox, and we certainly saw an example of that in the last slide, at least for the non-ESR Firefox. And just the engineering-wise, the reason why people seem to care a lot about this is they like their battle-tested C code, buggy bugs and all, right? And it's painful to sometimes rewrite everything. I would rewrite as much code as I can in Rust as long as memory safety was my targeted, like kind of the thing I'm trying to fix. But in scenarios where that's not possible, this is a pretty good way to go about doing things. And the upside is when you do this, you do not have a 4 a.m. O day that you need to get up and go and fix. And so that's kind of where things were as of 3-4 years ago. So I'm just going to give you a very quick kind of thing of the new stuff we're up to, stuff that you may not have seen in previous talks. Okay, what is it that we're doing with RLBox right now? I mean, clearly all of this at least kind of sort of works. Well, the first problem that we are running into in Firefox is sandboxing on 32-bit CPUs is super painful. And yes, Firefox does still support 32-bit CPUs. 32-bit x86 is supported. And you know, we have a bunch of smart people here. We can guess what the problem might be. 32-bit WASM does not have guard page support. It has only bounce checks. The takeaway is WASM running on 32-bit platforms is slow. Turns out that's not the problem at all, because apparently in the real world, it's okay for the software running on 32-bit CPUs to be a little slower. We want it to run, but if it's a little slower, that's okay. And so, and don't get disheartened by this. I'm going to show you how we can fix this even on those platforms, like right at the end of the talk, how we can even target those sort of problems. But it just turned out not to be the biggest thing. And instead, the thing that we had to reckon with is that when using WebAssembly in this context, the linear memory of WebAssembly, we cannot move it. Because WebAssembly obviously refers to all of its memory with offsets, which is great. You can move it, grow it, whatever. Firefox is going to talk about the same memory that WebAssembly is using with global pointers. And once it takes a global pointer to something, you cannot move it. At least you cannot move it easily. Which means the only way we can deal with this is to basically pre-allocate as much virtual space as we possibly could use, and then grow into it as we need. Not at all a problem with 64-bit CPUs. We have tons of virtual memory space. Huge problem on 32-bit CPUs. We have to guess what our maximum virtual memory footprint would be, and literally I have code that calculates, the font file size is 8 MB. I typically see a 3x bloat. All right, let's guess how much max memory we need, etc. So this is a little painful, to say the least. So what we've kind of started doing is asking RLBox to deal with this. And I'm just going to give you the intuition because the details are very involved. But if we can get RLBox to return smart pointer-like things into the WASM heap, we suddenly can deal with the fact that the heap might move, right? Because the smart pointer can keep looking up, oh, the heap is here now, the heap is here now. So on every access, it just adjusts to wherever the heap is. Now, this is all easier said than done. This could wreck performance, but we are seeing some positive signs on how to make all this work out well. So a second problem that we have to tackle is something I kind of glossed over very quickly, which is, if you remember, I said one of the 3 RLBox rules, sanitize the tainted data before it's used. This is kind of manual. And the story we had for everyone in 2020 is, oh yeah, the sanitizers are simple. Don't worry about it. It's 3 lines on average. It should be fine. We knew it wasn't enough. Everyone knew it wasn't enough, but this was the best answer we could give you. And not surprisingly, we got it wrong once. And there is a bug thread. And the person did receive a bug bounty because all of this code is bug bountied being a part of Firefox. And so we started this work which is, I'm just going to call sandbox auto-sanitizer, which infers or checks the RLBox sanitizers using programming language techniques. And the way to make this practical is actually kind of tricky and detailed. I'll talk to you offline about it. But there's actually some very interesting details on how to, actually make this work. And kind of like the proof in the pudding is it found another bug when we ran it. So we got apparently 2 sanitizers wrong. Now, I'm not going to tell you who in the group got the sanitizers wrong, especially when they're away and ill, but, Okay, so, all right, so that should kind of give you a little bit of taste of like all the stuff we're doing just to kind of use WebAssembly for library sandboxing. Now, one of the other things our group kind of broadly has been involved, including with Chris, is how do you use verification and other tools to ensure the security of WebAssembly? And the thing to keep in mind when you use WebAssembly is it gives you memory isolation if your compiler doesn't have bugs, if your runtime doesn't have bugs, that is to say WASI doesn't have bugs, and you're not worried about Spectre. These are the 3 caveats. And this is a fantastic attacker model for web browser security or application library security in general. Oh, I have an extra slide, sorry. But in another use case of WebAssembly, which is the function of a service platforms, this changes completely. So for those not familiar, the way WebAssembly is used in function as a service platforms is clients submit their code as WebAssembly modules and they're all run in a single process in the server. And that's actually very, very efficient because once you don't have a billion processes floating around, your server is super efficient. This model, however, is quite a bit different. Attackers in this world submit and run their own code, which makes things like Spectre a lot more, worrisome. So what we need is end-to-end security guarantees. And, how do we actually go about doing this? So, sorry, I think I messed up there we go, slides, there we go. So what we really want is to preserve WASM's memory isolation at the binary level when it's running syscalls and when it's executing speculatively. Now, at the binary level, we were involved in this work called VerWASM, which, that has been taken a lot further by Chris, and I think he might have mentioned some of that in the talk, so I'm not going to dwell on this. The short version is you can look at a binary produced by a WebAssembly compiler and ensure that all of the checks are in place. Turns out WebAssembly has just enough structure to make that actually feasible. And if not, you can always get a little help from your compiler with a little bit of hints. The other thing to keep in mind is we need to, and yes, this is work that is in NDSS 21, if you want to read more details. We also have to pay attention to the runtime. We need to ensure the runtime is safe as well. And the problem being, if the runtime calls the OS with essentially bad parameters, and the OS clobbers the memory that WebAssembly shouldn't have been able to access in the first place, what are you actually getting with WebAssembly, right? And the problem is, the POSIX spec is super complicated. How do you actually deal with ensuring you don't mess that up? And the one-line intuition of why we can kind of actually make verification practical there is it turns out you only have to pay attention to the part of the POSIX semantics that affects the WebAssembly memory isolation properties, which is a far tinier fraction of it. And so if you actually look at the code that implements this verified WASI kind of implementation, it's fairly reasonable. The asserts on top are not that complex, at least compared to other formally verified code that I've seen. So with this, and yes, this is work in IEEE S&P 23, if you want to read more details. And finally, let me talk about speculative safety. And the basic problem here is WebAssembly's security checks. I'm just going to say bounce checks, but security checks in general. It could be CFI checks, memory checks, whatever. They're all at the function granularity. So the moment you have speculative control flow, things could get bypassed. So we've come up with this construct called linear blocks, which basically says don't let control flow get between the security check and the operation that you're securing. So simple example on the slide. If you can't read it, what it says is, oh, look, I'm checking an index to ensure it's in range. I'm making a function called somewhere else. And then I'm loading from that location I just checked. Entirely reasonable code to run normally. Speculatively, funny things can happen the moment you have control flow, that call instruction. So the basic idea is, let's not allow the memory bounce check to be lifted that far up. Let's keep it closer to the use. As long as there's no control flow in between, that's fine. Additionally, when you check the index, we want to use speculation-safe checks, things like masks. And that's the high-level idea. This is one of the most technical and nitty-gritty kind of papers we've written, this Usenix Security 21. But it really boils down to a couple of core techniques and using them well, and this is one of them. There's another thing in that paper which, in hindsight, I might have mislabeled by calling it the register interlock. It's actually what it is a specter-safe WebAssembly CFI. Meaning you can actually deploy the CFI and get the CFI properties you want, even speculatively. And talk to me afterwards if you want me to kind of walk you through how that happens, but it's actually kind of cool. But and here's the other new bit, which is kind of the follow-up thoughts on this paper, which I've never actually, said out loud. But I think we actually kind of made a mistake positioning that paper, just because we focused on perfection, which meant the techniques cost all the way up to 200% overhead, which is great. We have a way to solve Spectre. That's not a great way, though. So what about an imperfect solution? The thing that I kind of realized in the few years after that paper is there is an imperfect scheme hiding in that paper that costs about 1 to 3% overhead that makes some to a lot of Spectre variants impossible and other Spectre variants much harder. So I really think we should think about deploying some of these sort of things in real compilers, especially in cases where people care about Spectre. We don't have to have them on by default, just in the cases where people care about it. So that is this kind of very brief overview of security. How are we on time?
We're good, actually. I should just be about to give you your 5 minutes. So I've done that.
Okay, it's 5? Okay, perfect. All right, so then let me get through this last bit very quickly because I want to get to part 4. So the last thing we've kind of spent a lot of time on is how do you make WebAssembly faster and more scalable. And there's 3 different techniques I'll very quickly tell you about. And the motivation here is WebAssembly isolation works, but there are some costs. Whether you're using bounce checks or guard pages, there are some performance overheads. If you want Spectre safety, it's even worse. And hardware can help with all of this. And let me just show you just a couple ways how we can go about doing this. So the first thing I want to tell you is this technique we've just dubbed Segue, and it's actually just been accepted into ASPLOS 2025. And the gist is, let's go back to x86 segmentation for WebAssembly. Now, the one-line description of x86 segmentation is it lets you describe the base of a region of memory and the bound of a region of memory. And every time you access that memory with a segment register like GS, you get a bounce check along with a base add, which sounds a lot like WebAssembly to me. You're essentially getting an operation that is access linear memory with all of the right semantics. The problem, segmentation basically went away for x86-64. This is all the top bit is all for 32-bit CPUs only. And the part they removed was the bounce check, which is a rather important part of WebAssembly semantics. But one of the things we played with is, well, let's just see what happens when we use the remaining part of x86 segmentation, the 64-bit segmentation, which is just the base addition. And it turns out this actually unlocks a whole bunch of low-level compiler instruction encodings and optimizations and cache impact of code sizes, etc. And when we actually tested this on real code, we found that in some cases it eliminated 75% of the overhead of WebAssembly. That XML parsing case, the hot path that we were talking about, 68% of the overhead goes away with this use of segmentation registers, which is wild. We did a workshop paper on this 3 years ago, and that we said 13%, and we were proud of that, and then we ran into this. So it is kind of an interesting point that this is where a lot of the overheads lie. And just to kind of give you a very quick intuition, the reason for that is there is a large drop in binary size. I don't know if you can read that. The median binary size drops by about 6%. So Segue is now supported by WAMR, WASM2C, and just last week, Firefox started using it for Linux as well. There's another technique called color guard that actually reduces the amount of guard pages we have to use. And this a lot of the insights on why guard pages actually were expensive was done in collaboration with Chris, and honestly, some of this was Chris's insights just directly, right? Now, I would like to talk to you about this, but in the interest of time, I'm just going to move on. Just say that guard pages sometimes have costs, and we know how to eliminate these costs. One of the techniques we can use is NPK. And of course, all of this is published. You can read all through the details or talk to me after. Happy to walk through it. And the moment you get rid of guard pages, by the way, makes running things like fast platforms easier because you have to rely on multiple processes less often. And the big thing about avoiding multiple processes is not the overhead, it's the simplicity. One process is just less, workload stealing, less complexity of dealing with multiple processes, pinning, etc. So where does this all leave us? We have improved the overheads, but it's not perfect. So the logical place to go is, what does a hardware extension on the CPU for WebAssembly support really look like? Well, you're not going to get a WebAssembly extension in any CPU. You're going to get an isolation extension. You need to be more general. Other CPU vendors tend not to accept it. So we went about trying to design this where we could extension where we could express data and control flow restrictions, interpose on syscalls, which WebAssembly doesn't need, but general code isolation does. And of course, we want to target both WebAssembly isolation and just isolating some binary you found out on the street and you just want to run on your computer now, right? It should work on both. Most importantly, we don't want OS changes because we've seen how long it takes for a hardware feature to get supported in OSs today. Currently, Intel CET, just as an example, 7-8 years before it got the patches into the Linux kernel, which is a tough road to kind of follow. So the key idea in HFI is we're going to talk about regions, which is a lot like segments. We're just given a different name to keep it simple. And we set up our regions, run the WebAssembly code. The WebAssembly code is restricted to the regions, then we exit. And the real trick in making all this work is you need to make the implementation work out for hardware vendors. The naive thing of saying, let's do big 64-bit bounce checks to support every possible use case will not fly, and they've told me as much. So our insight was, well, we need to take advantage of the domain. We need specialized regions. And we have a kind of detailed design walking through all of this and showing how we can actually use very, very small modifications on the CPU to support WebAssembly and eliminate virtually all of the overhead of guard pages, of the base edition, of almost everything. And best part yet, it's also Spectre safe. You at least can't break out of the sandbox if you're using this extension. And so if you kind of put this along the lines of compare it next to the other techniques we have, it really does seem to look pretty good. I do have a little caveat there, which is more for my own sanity. I'm not going to get into it. There is a very, very subtle and complicated way to perform attacks, which requires another solution. It is an open problem. We have an expensive solution, but it's not good enough. Anyway, this extension HFI, co-designed with Intel folks, co-designed with Revos, and also has input from fast companies, mostly courtesy Chris, and also input from the Google Chrome team, courtesy Samuel Gross. And the short version of that screenshot is HFI looks pretty good for Chrome's uber-cage custom hand-rolled sandbox for just-in-time compiled code as well, which is kind of a nice touch. So in the last 1 minute, 20 seconds, okay. Let me just tell you this. I'm going to throw something out there very quickly, and maybe I'm wrong. Maybe this is the hot take that's just wrong, but I just want to leave you with something, which is we have a lot of the early adopters of WASM. So who are the next adopters and why are they concerned? Well, I'm going to actually make the claim that compatibility and security are going rather well, relatively speaking. The part that I'm seeing a bit of a gap is performance, and so this is where we have a lot of work in progress. And one of the big things we're trying to do right now is compare WebAssembly SFI to classic SFI tools. And WebAssembly actually has a lot going for it in terms of control flow, in terms of quick transitions, all of which is formally proved, work with Conrad, and POPL'25. But it also has a bunch of open problems. It cannot eliminate dead reads. We still don't have a great solution for MEM64. And WebAssembly operates on offsets, which means we baked in overheads right at the beginning, which we cannot eliminate. And there's also this other problem of you often have to copy data back and forth, which we have a partial solution to, but it's work in progress. And here's kind of the thing I want to leave with this room. I've tried a bunch of system solutions to the open problems on the last slide. They don't work. The only solution I actually see that's going to work for those problems is now a type-based or small extensions to WebAssembly, which is a pretty good note to end my talk. Please think about this and come talk to me. Happy to take any questions if we have time left.
Thanks so much. We would never know that basically this time yesterday you were just agreeing to fly over and start this talk. So thank you so much again for doing this at short notice. John, would you mind swapping in your laptop right away? And as we do that, we'll take a few questions.
Thank you for the talk. I really enjoyed it. For hardware fault isolation, I saw a bunch of asterisks there in terms of, what, and you also mentioned that you added some caveats. I was wondering if you could speak a little bit more to that. Like, what do you consider to be the risks?
So the asterisks, there were two sets of asterisks. One
Maybe
was
the first one, the first.
Yeah, first one was what does adoption look like? And the truth is, I don't know what Intel has expressed interest to me. Just as it's interesting. I do not know what their expectation on actually building it out is. You'll have to ask someone at Intel. We are working with RISC-V to make this in a TG to actually make this a formal spec. In terms of security, the HFI attack that's possible is not where code inside the sandbox reaches out and touches memory it cannot have access to, but rather it's this complicated attack where outside code can, prime the branch predictors and confuse the code inside to leaking its own data. It's a spectacularly complex attack to pull off, but it is technically there. So which is why I think it's a technical asterisk. I do not know of a single case of a real world attack that has come close to this level of complexity.
So we just have to give it a couple of years.
You'll see a paper about it. I do not know that you'll see a real world attack about it. That's my guess.
I'll ask one quick question then. If there's one feature you could magic into WebAssembly without having to carry out the standards process, what would it be?
Special type. Oh, sorry. One feature that I could magic into WebAssembly spec, a special pointer type, useful for half the things I've talked about.
Okay, thanks so much. One last thanks to Shravan again. Okay, so for our next speaker, we have John Short, a PhD student at the University of Ottawa. John, please take it away.
Thank you. So what I'm going to talk about is essentially, we're going to say the execution cost of a WebAssembly function is the number of instructions an interpreter would execute when running that function on its inputs. So clearly this is a woefully inadequate definition of execution cost, but let's go with it and see where it takes us. I'm going to talk about the motivation for this work, some of the work that I did earlier for my master's thesis, the approach to the work that I'm doing now, and what's next. So the motivation effectively is that WebAssembly runs in a sandbox, and what's run is arbitrary code. So shouldn't the host be able to know what the cost of running that code will be and make a decision about whether or not to run that code or not, depending on the cost of running that code? Today, the method that's used primarily is to run the code and kill it when it's consume the resources that the host would allow it to use. It's too late. In strong terms, the damage is done. So if we knew beforehand what it was going to cost, then we could mitigate that damage. So for my master's thesis, I kind of outlined an approach to bounding the cost of a single WebAssembly function, not the entire call tree, just that single function. And the things that I used were things from compiler technology, theory of programming languages in general, including basic blocks, flow control graphs, and iterating over flow control graphs, symbolic execution, slicing to find loop constraints, and understanding the parameterization of loops. I also implemented all of this in OCaml, a utility called WANalyze, which was about 5,000 lines of OCaml, that included a binary parser for WebAssembly modules, which I kind of recommend as a project to anyone who wants to have a deeper understanding of WebAssembly. A symbolic execution engine, because in order to understand the performance of loops, I needed to understand symbolically how the constraints in a loop were being constructed and operated on, and all the other concepts from the previous slides. In the end, I was able to produce numeric bounds for non-looping functions, which is kind of a straightforward thing to do, and symbolic bounds for some looping functions, assuming that we could solve the loop constraints, assuming that we had a solver that could solve the looping constraints, and there's a lot of literature about that, but assuming that we could do that. And one notable thing that happened here, I tested this on a small but large, small number of programs, large programs, medium to large size WebAssembly modules, including everything from a Bitcoin miner to Doom and AutoCAD, and combinatorial explosion of the paths, the possible paths within the body of a loop rarely actually occurred. I set an artificial limit of 1 million possible execution paths through a loop, and I would say in less than 5% of the loops that limit was achieved. So this was kind of encouraging. Okay. So when I finished that project, what remained to be done? When I essentially defended my master's. So one of the issues, what I did was, there were a lot of results that I stated as facts with arguments, but not what I would consider to be a proof. And so I wasn't happy with the sort of rigor of what I had done. I needed to implement those loop solving techniques from the literature, and there's like 30 or 40 years of literature on this. I wanted to extend it to do the full call tree of a function and do more performance testing and performance measurement. So now I'm focused on the first point on this slide. And so I actually was aware of the work that Conrad had done in mechanizing the proof of preservation in progress. And I picked up the GitHub project for that last year and looked at it, and I kind of realized that there was also something very interesting in this, which was a generated from the COC implementation of a WebAssembly interpreter. So this is interesting. How can I use this to further my goal of making my own work more rigorous? So it's kind of clear at this point what to do. I need to formalize in COC all the things that are needed to implement the bounds checks that I implemented in my OCaml code in COC, leveraging the definitions, the COC definitions that are in WASMcert today, and by the way, making sure that I don't break the things that WASMcert proves. And you know, after playing around with it a little bit, it became kind of like essentially building and running the project. It became clear to me that this was, not hard to do. I could break the proofs that were in there by doing stupid things. So as long as my reasoning is as long as I haven't done anything stupid and the proofs still work, then everything that I've done should be fine. And then furthermore, I could extract to OCaml a program that does what the OCaml code that I have today does, but with one significant benefit. So I dug into it, and here's just a snippet of code in Coq with the things highlighted in green that I reuse from the WASM cert project. So basic instruction is the long inductive definition in Coq that defines all of the instructions in Coq. So essentially, my definition of basic block is a list of instructions in WebAssembly that contain no control flow, no instructions that can cause a change in or be the destination of a change in flow control, with no such similar instruction in the body. It's a simple and obvious way to define basic blocks. And then I defined two functions, is basic block and basic blocks of expression. So that's essentially taking the body of a WebAssembly function and producing the list of basic blocks that constitute that function body. And then I have to prove a lemma that my definition that these definitions are consistent, that I'll correctly produce a thing that is a list of basic blocks from from the function that creates the list of basic blocks. So this is a flavor of the kind of thing that I have to do. The other kind of thing that I have to do is that I'm studying flow control graphs, and I'm analyzing the costs of executing this is a flow control graph of basic blocks. I'm studying the cost of executing the cost of executing the basic blocks in this graph, and if for a moment we ignore the fact that there are loops in this control flow graph, we can see that from a graph like this that contains no loops, we can easily derive the cost of the function. To allow analysis of loops, essentially, I aggregate the basic blocks that make up the loop into larger blocks that I call loop blocks, where a loop block contains all the consecutive basic blocks within a loop that don't that are inside the boundary of that loop. And this is an example of this is actually a diagram produced for a bubble sort function that contains a loop and a nested loop, and contains some preamble code. So I need to define this kind of structure in Coq and then write Coq code to do the analysis of this structure to discover what I need to know about loops. So what I need to know about loops actually comes from the fact that there's really only two graphs or two forms of graph that a loop structure in WebAssembly can have. And essentially it's, we check the condition of the loop, the guard of the loop, and branch to the top of the loop, in a loop that continues effectively, or we branch out of the loop in the case of a loop that breaks. So I should say that to do this analysis, I've taken a loop and created a copy of that loop, a control flow diagram for a copy of that loop for every possible path through that loop. So this is where the combinatorial explosion can occur. But essentially, I have a very simple view of a loop. It's, it kind of looks like this, like one of these two things, and it is amenable to an analysis that's kind of simple when we look at it just in this form. And so the things that I need to parameterize the loop is the condition for the loop continuing, which is the condition on the branch if statement. I get that by symbolically executing a sliced version of this code. And it's sliced because I know the variables that are in the condition. Variables, I mean in a very general sense. You know, it could be memory, it could be global variables, it could be local variables. I know what the initial values of this variable are when we enter the loop. And from the slicing, I also know how the variables are updated as the loop executes. So this essentially gives me, I think, everything I need to give to a solver to tell me how many times this loop will execute. The problem is that this is all symbolic, so that's going to be challenging. So why am I doing all of this when I have an OCaml program that already does it? And of course, the answer is to get some rigor in what I've done. And specifically, the benefit of the rigor will manifest in the fact that I want to be able to prove in Coq this family of inequalities. So what these inequalities, so you actually, obviously you read these inequalities from the bottom up, not from the top down. So these inequalities are sort of a set of recursive, nested inequalities that go from determining the cost of a basic block, which is simply the number of instructions in the basic block, through the cost of the path of a basic block, which is a path made up of basic blocks, which is essentially the sum of the costs of the basic blocks in this path, and then proceeding upwards to the cost of a loop, and then to the cost of a function. So and you'll see that there's the presence of this magic in 4.2 n of e and x, which is for a given loop denoted by e, and inputs x, how many times that loop iterates. So this is something I need to solve, but essentially, if I can prove all of this in Coq and generate an OCaml program that produces the cost on line 4.1, which is the cost of the function, then I've achieved in building a framework that allows this cost to be determined in a verified way. So once I've got all that done, what will be left to do? I'll need to implement other things that I talked about earlier, but I'll also be able to compare this to my existing OCaml implementation. So I'm kind of interested to see where that will fall from a performance point of view. And there are other issues when it comes time to the implementing the entire function call tree, obviously. And I should say that what I've done so far is strictly based on WASM 1.0, and obviously there's lots of work to do for WASM 2.0. So my conclusion is this. WASM has a minimal spec from the point of view of program analysis, because clearly we need to add many concepts in order to do interesting program analysis of WASM programs. I think that WASM Cert is a good starting point for this, and I think this project, as I work on it, will bear that out. And this gives us a path to verified program analysis for more than just the problem that I've described. This in a sense is a prototype or an example of a problem that can be solved with this approach. And I'm hopeful that I'll be able to use this as a proof point to espouse that approach. So as Conrad said, I'm a PhD student, third-year PhD student at the University of Ottawa. I'm working with Amy Felty and Anil Somayaji as my advisors. They've helped me with this work. And with that, I'd like to thank you for your attention and answer any questions you might have.
Thanks so much. That was a great talk and perfectly in time, so we have time for some questions.
I've got a couple of questions. So first, you were a bit disparaging about your cost analysis at the beginning in terms of saying, well, this is what I'm doing, and you know you didn't sort of justify it. And sort of now stepping back, and you're not an MSc student, you're a PhD student, what are you thinking about sort of better cost functions or properties?
Well, I mean, specifically, this is costing WebAssembly instructions. And so, you know, those get, in the use case that I'm thinking of, typically get compiled into native machine code, which may or may not have the same characteristics as the interpreted WebAssembly code. So that's one point. The second point is that, you know, clearly the cost of a memory load is significantly different than a cost of a register move or a multiply instruction compared to an add instruction. So there's a granularity there that in a useful tool would need to be expressed, and I'm okay to ignore that because, you know, I think that's something that could be added in later, you know, and when all is said and done.
And also another question. So my student Rao and Conrad and I in POPL have got a paper where we have an interpreter, and the point is when you extract all the proof gubbins doesn't cause any problems to do with performance, i.e. what you hope to get from the interpreter is what you get. And we had to work quite hard to get that done. And what do you think regarding your analysis, cost analysis? Is it entwined with the WASM cert? So when you're extracting, are you going to lose performance compared with the one you did directly in OCaml, or are you going to?
I'd be stunned if I didn't lose performance.
Yeah.
Right. I mean,
yeah.
I don't know concretely today what that might be.
Yeah.
But I would expect.
Yes.
That I will. And you know, the good thing about having the hand-coded OCaml implementation is that it gives me a concrete target that I'll work towards and understand. So yeah, I look forward to getting to that point.
Thank you.
Yeah, I guess, you know, as is quite obvious, I think this is work in progress.
No,
this has just begun more than anything.
So I have one last question, but maybe while you're answering it, can we get Lucy up onto the stage to swap the laptops? So my just final question is, I liked your kind of point that you focused on this cost analysis, but that doesn't have to be the only thing you're thinking about when building this kind of verified tool. what would be the second analysis you would be looking at if you had
Oh.
time to do one more?
Yeah. I think I'm drawn to things like taint flow and security related issues. I made a note as the last speaker was talking that memory consumption, it could also be an interesting thing. You know, if there's a loop that's allocating 2 gigabytes of memory per loop iteration, and I can tell you that that's what happens, that'd be pretty interesting. So those are kind of very direct. I think, you know, more generally, there will be other interesting program analysis tasks to undertake. I'm confident of that. Thank you.
Thanks very much. Let's thank John again for his talk. So our next speaker will be Lucy Menon, who is a software engineer at Microsoft, but maybe in a few seconds. I have a backup laptop if it's needed, by the way.
Yes, I do have Type-C, but kind of. I've used the Type-C before. I've used it before. No, I guess this connector really doesn't like me. Oh, yeah.
Okay. Can you email your slides to me?
Yes, I can do that. Sorry.
No, this is why I've got the laptop. Let me get into the business of whether it will actually work.
Do you have, do you think they can do PowerPoint?
Oh no, it has to be the PDF rendering. Does that create problems for you?
Yeah, a lot. I have a lot of animations.
You don't have an HDMI keyboard, right? You can try this second way to use it. Did you actually,
Yeah,
let's
so
try
I
the
do have,
connector
we
directly.
did try that as well.
Did we?
Yeah.
Oh, okay.
So much you could try and save the million. Which million? Let's see.
That's definitely not happening.
Yeah, no. Doing the same thing as it was before.
So, okay, how complicated are your slides? Can you just render them into PDF and email them to me?
I have a lot of, I sat through a lot of stuff. In particular, like.
They'll just turn into separate slides.
So the ones, so they don't on this point, so they hit like buttons but in the final state, which is not really useful.
Maybe better than nothing.
It would be better than nothing. I'll do like, let me see what I can do. What's the name of this again?
Just CNRD, WTC. Yes, I think maybe let's be a little less psychedelic in the meantime.
Sorry. If you can import it into Google Slides, it might work better, actually.
Well, then, in that case, you should send me the Google Slide shareable link, right?
Okay, yeah, let me see if I can, well, I don't have.
However, they talk to the AV committee to send us help per sheet.
Okay,
But
well,
you
multiple
can-
paths
meanwhile
being
you can-
pursued.
Yeah.
I'm so sorry.
No, it's totally fine. But let's, I think we need to make the call that you just send me the PDF.
Yeah, well, I did send it, I sent you something.
Okay.
Let me see, if I send you the connection. Oh, and I can do, okay, cool, I can do open button, which is that might also, yeah. So I think so, I tried to send it to you, but I just realized I didn't.
Oh, I see, you sent me the raw PowerPoint file. So actually, maybe I can use my,
Yeah, it might.
I'm going to see if I can upload this to like Microsoft Office Online.
Oh, yeah, because that is what I was using, so if you can do that, that would work fine.
This one notice this tenant Microsoft. I can't use the admin installed into it.
Okay, great. I guess.
Can you just send me the PDF at this point?
Yeah, okay. So let me, so I think I know why that happened.
we have some people converging. So while I am working with a possible backup option, see what happens when this is connected to this. Yes, this. Yeah. Oh well,
You
just
can
in,
try
in
the
any
HDMI
capacity connect to the laptop.
Oh, that's interesting.
Okay, I have a pretty nice rendering of the slides. Is this animated the way you'd want it to be?
So that slide is the big question that I have about. Let's see. Yeah, so that slide should be like 10.
Okay.
But
Do you think you could
I
talk
can
through
probably
it?
manage it.
We're gonna go with the backup. It's gonna give us some animations.
I don't.
This is the only computer this has happened to. There's always a first one. It's fine. Okay.
Is it working fine?
This one is working fine. We'll lose a few animations because I don't support the right format. I'm sorry about that, but we'll make do. I'll try and give you a few extra minutes on the side. We may need to cut a tiny bit, but just watch for my signals.
Is it supposed to be a black screen?
What's probably happening is, let's try one more time. I think because it was on full screen mode, it wasn't letting me do the extension, but now it should work.
I didn't touch it. Let's check.
An actual PowerPoint format that you can.
It's popped off. Okay, so sorry, this is not perfect, but I think this is the best we can do. So,
All right.
because it's an extension, you'll have to press the left and right and look at the screen to see what slide you're on.
Okay.
Sorry about that.
think that works.
Remember to stand here so that camera can.
Where's the cam?
There. So.
Okay.
I guess you need to stand here a bit. Let me just check.
Okay. Yeah? Okay. You can switch it back. I tested that it works. When did you get in contact?
I got in like 9 p.m. yesterday.
Okay.
So I took a bunch of melatonin. It seems to have shocked me into a rhythm that works for this.
Are you here for the rest of the week?
Yeah, I have a student giving a paper at the main campus later.
That's cool.
Yeah. I know, God, I have like to go do useful things.
That's really cool.
One of them is even going to finish the references open in the threads. If we can finally get that to base 5.
I found that it's very hard for me to like not do the things I was doing, so I end up doing two things and doing none of them well.
I'm very disciplined about not doing personal research because I think it's hard to justify right now given the number of people who think it's different things that
No, I think for us the problem is also that because Adam's a new burger, we just don't have the backfill, so I do it or nobody does it because everybody else has a thing that they're already doing. And I should just drop it to the floor, but I don't.
So presumably the remote talk will just seamlessly happen?
Yeah, so to my understanding, a bunch of AD volunteers are going to rush in and run the remote talk when it comes time to answer.
Okay. Do you know about this?
Yes.
You know that the second talk is remote?
Did you need to finagle people for dinner?
I've been kind of slow about that, but that's something I'm going to sort out hopefully during this session. Finding a place.
Oh, do you need help?
Do you have advice? I have a short list of places from the conference organisers that do you think...
If you know the number of people, I can make an online reservation after my talk. I can.
Okay, let me, during your talk, let me do a little bit of...
Let me know if you need help. Yeah, I don't want to preempt you, but I'm happy to help you. Because I have all the apps that make the...
Okay, then that might be useful. The big thing would be, so when I've done it in the past, the reason I did it is because when people inevitably join on, it's on me to expand the booking, and then it doesn't, I don't have to put that on you. Let's see what the numbers look like.
It's also a weekday night, so I'm hoping that it's not a big issue. And we also don't want to go too far. It's so cold.
No, I think so. The backup is there's a really nice diner on Street Play.
Okay.
We went there yesterday, but that's not everyone we could go again. But that's like a very safe backup in case other things don't happen.
Does he have a roommate? I know his roommate. I guess we could. Is there an easy way to call the roof?
There's an easy way to hit them.
Knock on the door.
You could also get the reception to call him.
Yeah.
Like a good.
But then I have to miss your talk.
Yeah, don't do that.
Here's Frank's talk.
That's true. I could do that. Yeah.
I think we are going to start on time though, because otherwise it's going to
Sounds
be
great.
relatively
Yeah.
late, because the AV people are going to come expecting.
I'm right here. I'm happy to start whenever.
Okay, hello everyone. We are going to get started. Welcome back from lunch to the third session of the WebAssembly workshop. I am delighted to introduce Deepti Gandluri, who is a manager at Google. Is that a fair way to introduce you?
I don't introduce myself that way yet, but sure.
Deepti is a very important WebAssembly person at Google, and she is going to talk to us about her work on WebAssembly at Google. Take it away, Deepti.
Thank you. Hello, everyone. I'm Deepti. I'm a software engineer at Google, and I lead a lot of the WebAssembly standardization efforts on the Chrome team. WebAssembly is close to my heart. I've been a part of the community for a very long time, so it's a pleasure being here. So in this talk, a lot of what I am hoping to do is talk about WebAssembly and the web, set some context around how WebAssembly fits into the broader web ecosystem, talk about why performance matters to us, and then lead into some performance extensions and memory utilization extensions, and talk about open questions. For a lot of this talk, I'm hoping to not cover the problems we've already solved, but talk about some of the future-facing and open questions that we have going forward or see into the future. So to understand a little bit more about how WASM fits into the web ecosystem, I want to talk a little bit about the history of WASM. This is an incomplete history, so let's start with native client way back in 2008. I've abstracted this time chart to just significant events. I'm sure there's stuff here that I'm missing. So way back in 2008, Native Client was announced. Native Client is a sandbox for running C and C++ code in the browser efficiently and securely. When we jump forward a few years, Portable Native Client Pinnacle was announced, and the Pinnacle extends Native Client with architecture independence. So somewhere around the same time, Emscripten started as a research project. Emscripten, for those who don't know, is an LLVM or Clang-based compiler that compiles C and C++ source code to WASM now, but back then the primary target was JS. And then ASM.js as well, primarily for execution in the browser. So around this time, kind of the 2013 timeframe, we saw a lot of games and applications being ported to native client or compiled to JS using Emscripten. But both of them had their own disadvantages. So Pinnacle worked only on Chrome, so it really wasn't very portable. And with the Emscripten and ASM.js pipeline, you had to do some very careful optimizations, very careful things to make them performant, and so that you don't fall off performance cliffs. So from 2013 to 2015, a lot of the tooling teams in these companies got together and started working collaboratively, and WASM was announced in 2015 and then released in most major browsers in 2017. And now we're a long ways away from 2017, and a lot of things have happened since then. We've extended WASM with threads and atomics, fixed with SMD, exception handling, garbage collection, memory 64, hopefully JSPI coming soon. And this kind of the 2025 plus portion is what I'm hoping to talk about today. So I am representing Chromium here. So I want to talk about the guiding principles of Chromium in terms of abstracting it a little bit away from the runtime itself. So there are 4 guiding principles. Speed, because the speed of rich web applications is really important to us, and one way we kind of service that is developing our own JavaScript engine called V8, which is what I work on. The speed of page display is also quite important to us, and which is why we have our own rendering engine, Blink. We also pay attention to the speed of user interactions from starting the browser to common tasks like clicking a button and kind of just minimizing the lag everywhere. So the other thing here is security. We want to provide the most secure environment for users. So security should be usable. So if you have evil.com, you don't want a permission that says, do you want to go to evil.com? What you want to be able to do is have consistent permissions that actually default to doing the right thing by the user. Stability is also quite important. Browsers are now a lot more than just content viewers. They're a platform in of themselves. They're ubiquitous. Everyone uses them. So we do have a responsibility to make sure that they're stable and backwards compatible. The 4th thing is simplicity. Simplicity can mean a lot of different things. In the context of UI, it can mean just a simplistic interface for people to interact with. But even when the technology is sophisticated, we want to have a very simple abstraction that we present to the user. So in the context of WASM too, this is important because when we develop things where the complexity is in the toolchain or the engine, what the developer sees at the end of it should be a simple and easy to reason about abstraction. So this is something I have here to talk about how WebAssembly fits into the Chrome's multiprocess architecture. So at the top here, I'm going to wait for it to switch back. But at the top is the browser process, and the browser process coordinates with all of the other processes. So you have the GPU process, the renderer process, the plugin process, the storage processes, the UI process, and the browser communicates with all of these processes. So for the renderer processes, so in the most simplistic way to think about render processes is that each tab gets its own process. The advantage to this type of architecture is that if one tab crashes, the other ones stay alive. This is also really important for security and sandboxing. So if you do have if you do have some sort of a security issue in a process, that it doesn't leak and affect the other processes. So one thing important to mention here is site isolation. And so I talked about the simplistic way of a tab and a renderer process having a one-to-one mapping. That's not always true. What you actually want to isolate on is based on sites. So V8 and Chrome's JavaScript and WebAssembly execution will be in the renderer process. Because processes have their own memory and come with their own infrastructure, you might have multiple copies of V8 running at one time, and that kind of increases your memory bandwidth, but I think the trade-offs here are something we're comfortable with. So the reason I bring up this type of architecture is we're going to talk a lot about performance in the next few minutes, and I want everyone to understand that performance has a lot of nuance. While the execution or the runtime itself is actually a really critical component to performance, it's not the only component. The browser VM does have to talk to the GPU process or other processes, obviously through allowed APIs and interfaces, but that also adds overhead. So sometime when we kind of introduce a lot of performance improvements to WASM kernels or are only looking at WASM performance, we do have to step back and evaluate whole application performance, because in a sense, that is what we care about. From the perspective of the WASM team, we have 3 North Star metrics that we look at. We want to enable applications to leverage the computing power of modern hardware. And this mostly applies to linear WASM, and we've seen a lot of this come true too with Adobe, with Autodesk, Unity, a lot of large native applications being ported to the web via WASM. But we don't want to limit WASM in that way. We also want to be able to expand WASM's reach by bringing featureful managed languages to the web, and critically with rich interop. The other thing that we understand too is that the success of a language or a bytecode format, as it may be, depends on the strength of its ecosystem. So we will also want to enable an ecosystem of WASM libraries, which will result in high quality applications at scale. So a lot of what we're going to talk about is probably going to be in service to the first of these goals, which is going to be focusing on compute power. So I want to talk a little bit more about performance and specifically why it matters. So there's 3 reasons why performance really matters, and there's a really good blog post about this on web.dev if anyone's really interested with detailed case studies and metrics. But the reason performance really matters is retention. Retention, conversion, and user experience. So websites that load really quickly and respond to user input tend to retain more users. So as an example, BBC found that for every additional second that a user had to wait, they lost 10% of users. Slow sites have a negative impact on revenue. Fast sites are shown to increase conversion rates. So there's a direct correlation of revenue increase and conversion increase of the amount of time you spend on a website if its performance is much better. The performance is a really foundational aspect of good user experiences. We ship a lot of code. Browsers have to use megabytes of users' data to download this code, and especially when you are on low memory devices, the user experience can be quite terrible. So in service of this, a lot of what we are looking to do, I talked about how performance is very nuanced, but there are very few cases where you can get performance for free. And adding compute extensions to WASM is one of those things because it's very self-contained and you don't actually have to do anything to be able to enable it. The toolchains will support it, the libraries will support it, and the applications will get it for free. So we've had a lot, over the years, we've had a lot of requests for different types of performance extensions. I know Shravan in his previous talk talked about SIMD, and one of the things that's interesting there is SIMD is based off of SSE 4.1, and that was released, I think, in 2006, so it's several years ago. And now that when we look at native performance versus WASM performance, the benchmark that we want to be around at is maybe 60 to 80% of native, but compared to the latest of hardware, especially on newer hardware, performance that we see is only about 25 to 50% of native, which is kind of a sad state to be in, unfortunately. So what we're looking at over time is how we can get this, how we can get performance of WASM up to scale. And this is not always easy, and I'll talk about that more. So a couple of things we're looking at is two different types of half precision values. We're looking at extending WASM with FP16 values, which is a compressed version of FP32. It has smaller dynamic range, but higher precision. We're also, FP16 is something where we have an end-to-end working prototype in the tools and in the runtime, and we're working on some early benchmarking. We're also kind of been looking at extending WASM with BF16 operation. And BF16 is quite efficient. It prioritizes a wider range by allocating more bits to the exponent, and it trades off precision for range. In a lot of ways, that type of precision isn't quite as important for the applications that do care about lower precision values. So in terms of some performance evaluations, compute kernels that extensively use FP16 demonstrate performance wins of 75 to 125% over what's currently in WASM. So this is, when I talk about, I also want to differentiate here between compute kernel performance and application performance. So we always want to see a direct mapping. When we see compute kernel performance improve, we also want to see application performance improve. In some interesting cases like RelaxSimD, we always didn't see that map one-to-one because you could use sparse data and then that affects your overall performance. So in this case, though, application feature performance improvement of 60%, and it also does reduce model size by 50%. I do want to mention that speedups here are specific to ARM64. They are challenging for consistent performance across x64 just because of varying degrees of hardware support over the years, and it still translates pretty reasonably well to the latest hardware, but we're still doing some work there. We don't have prototype numbers for BF16 because we don't have a full prototype yet, but we do have really strong interest. The BF16's wider dynamic range reduces the risk of underflow and overflow that FP16 can sometimes have. BF16 is designed to be compatible with existing FMA hardware, and that has better portability. And the thing about BF16 too is that there's a lot of new research that talks about compute kernels and BF16, and especially for ML workloads, a lot of what we're looking at, we see a lot of research optimizing using BF16 over FP16. FP16 is still important for general interop, I think. We've seen that especially if you don't have FP16 support for multiprocess architectures or browser VMs that do use different types of compute units, not having that supported on one compute unit means that you have to fall back to FP32, in which case the performance is pretty bad and you do incur a significant cost of conversions. So there are general advantages of lower precision values. You have, it takes less memory, less compute, and there is also more parallelism because you're able to compute more data at the same time. So we've talked about leveraging hardware, we've talked about applications. Another thing that I want to talk about is ease of use and ease of programmability. A lot of what we see a lot of the challenges that come with compute units is that we are introducing features incrementally. Now, that's really problematic in an environment like WASM where you don't have consistent feature detection. And the problem with feature detection, when I tie it back to performance, is that with the ever-expanding feature matrix like we have right now, what you have to do in the user space is send small, tiny modules and then pick based on feature set what binary you're going to ship. So not only do you have to have multiple binaries, you also incur runtime cost of figuring out which binary you want to ship. So you pay a load time cost, and you just have to ship multiple binaries, and the user experience just isn't that simple. And the reason we're in this place too is because there isn't quite as much consistent hardware support as we hope for some of these new architectures. So WASM does have like an ideological issue here of like, what would we do if we did want to support high performance extensions? Now, not everything falls into this bucket of not having consistent support, but at least the ones that applications really care about these days do fall into that bucket. So we've talked about this several times in the CG as well, and I just want to like talk about a lot of the options. We've talked about, emulation detection. So you have scope per feature, you have a feature, and then per feature you can decide whether it's emulated or not. And could long-term feed into feature detection. But the problem with something like this is emulation detection isn't always easy. Where do you draw the line? There's, especially when it comes to x64, you have several layers of hardware features, and it's hard to say what is emulated and what isn't, and it could mean different things to different people. We've also gone down the route of extensive runtime optimization, especially like revectorization in the engine, because we don't have 256-bit support. What we could do is look at tight loops of 128 bits and then promote them to use 256-bit operations. That sounds nice in theory, but in practice, it's brittle just the way pattern detection everywhere is. It also runs into some interesting cases when you're looping around loads. There's edge cases where we wouldn't be spec compliant. And in general, it's also really hard for applications because they now have to feature detect when this is available and when this isn't. So you might want to ship different code if you know that you have 256-bit support versus not. So there's still a lot of things. So we have a prototype of this, but we also don't know exactly how we would get applications to use it because there's a lot of challenges around that. We could also bypass standardization altogether and have shared conventions, but this is an option I don't necessarily like because that usually means that's ballooning and fragmentation in the ecosystem. We've been talking about an incubation framework. I know a few folks in this room iterated over what it would mean to have hardware-specialized WASM or some set of incubation opcodes or built-in or import functions. While in theory this is nice, but WASM is just supposed to be an abstraction. Like you can solve any problem with an indirection, but the question is always, do you want to? And so it's interesting. It's not. There's no straightforward answer. Obviously, the easiest thing here is to do nothing and decide that we don't want performance, and WASM is just a target for different languages on the web. As a browser VM person, that's really hard for me to accept, but that it is an option. So as I said, there's no easy answers, but I do think that there's a lot of room for experimentation, and I have hope that we might find something that we land on here. Another thing that I want to talk about is the memory footprint. So the current linear memory model is very simple and portable, and it's proven to be really effective for, for a large number of use cases. But it also imposes some really unfortunate restrictions on serious WASM applications. So you can't free memory, especially when you're interacting with the host environment, because WASM owns all of its memory, a lot of what you have to do is copy back and forth. So one of the proposals we have that are fairly early stage is memory control, which the goal of memory control is to provide fine-grained control over WASM memory. So what we want to be doing is reducing the impact of copying into memory. And especially if you have a large application, like I can think of an application that is like photos, that is processing a lot of photos and videos, you don't actually want to have large copies of large allocations sitting around and consuming memory. You also want to give applications just better control over their memory footprint. So you want to be able to allow applications to discard memory when it's not in use, and give them larger address space to use. You want to provide APIs for memory protection. And these are all things that you're able to do really seamlessly in native applications, but we do have hurdles when it comes to WASM that we're not actually able to do these things. Now, it's a little bit of a trade-off here, because every time we touch the memory layout or any of these WASM any kind of the buffer allocation things that we do, it is a very security sensitive surface. So we want to touch as little as possible here, but while also getting as much as we can out of it. So we have some proposed API functions here. We've been iterating over this with folks over on the WASI side as well. A lot of what we want to be able to do is when we have API functions, that they are consistent across JS and WASI API. So when we do want to bubble something into the core spec, that we have a consistent way of doing it. So what you see here is what we're looking to introduce are a few different things. A memory map descriptor, which would be a JS wrapper around a file descriptor of the operating system. Which could then be passed into memory.map, which is an additional method on the WebAssembly.memory that can map the memory represented by the file descriptor. We also provide memory.unmap, which is a method to remove mapping starting at the address offset and continuing for size. Size here is represented in a number of pages. So we do have an early prototype of this. A lot of what we're hoping to do is actually gain some application data. This is, again, we don't have a very secure and safe application. What we're looking to do is get the minimal prototype out and see what is the maximum ceiling of performance we can get. By our estimates right now, we expect to reduce overhead by 20%, but a memory like the overhead of memcopy is easier to measure than a memory utilization itself, because that is very application dependent. So if you are looking at some sort of thing, or you have an application that would be interesting for us to experiment with, please reach out to me, and we're happy to help with experimentation there. So, but there's a lot of open questions around this. If we were to propose something that is exposed to the core specification, what would it look like? We could, there's the option that I presented is that we limit exposure to the core specification and have only API functions. Now, the problem with that is you still have to have some notion of a special memory, because you're going to be seeing reads and writes that don't originate from WASM memory. It's also possible that we could introduce additional conditions that allow trapping, and the core spec has to have some notion of how to be able to reason with that. And also, data segments present a tricky challenge. Active data segments can't write into memory unless it's mapped. So we're going to need anonymous mappings if we want to be able to give more control over the memory. So this is something we're going to have to think more about. As I said earlier, this area is definitely one that is quite full of open questions. So ordering of memory calls on shared memory, we don't really know what we don't know. All WASI calls have undefined behavior, and this also is very OS dependent. Do we want to do anything to contain this type of undefined behavior? Especially for the non-determinism introduced, we want to figure out how we want to expose, how we want to think about how individual threads observe memory accesses. Maybe there really isn't that much to do here. But especially when you have several of these calls happening from multiple threads, should we be providing any guarantees for safety? And do these operations have to be atomic? They're not always guaranteed to be atomic by their OS primitives on Windows specifically. I think Linux makes some guarantees, or doesn't say it, but experimentation, you can tell that it is. But on Windows, this is not a guarantee that we can provide. A lot of what we've been experimenting with recently is overlapping mappings. I think that we're definitely going to be providing overlapping mappings, even though they're not consistently supported on Windows platforms. Different versions of the Windows OS have different primitives for overlapping mappings. And I think this makes it easier in a way, because a lot of what we had to reason about when it came to memory control is what should happen on an unmapped. And if you have a region of memory that's fundamentally inaccessible right in the middle of memory, it raises a lot of interop challenges as well. So what we've landed on now is that this is something that is natively supported anyway for applications that are mapping into their own address space. It can be trusted to map over an existing mapping. This is supported by existing syscalls on Linux and Mac. So just generally disallowing it seems like you would introduce extra overhead because applications then have to unmap and then map again. So yeah, a lot of, especially when it comes to performance, we do have several open questions. So especially for compute extensions, what is a sustainable way for adding new numeric extensions, and how do we reason about the performance and the complexity trade-off? As I said, feature detection has kind of been really hard to nail down. We've had multiple different attempts at a general feature detection, at conditional compilation, that haven't really made a lot of progress. In terms of WASM, we're a little bit loose about what we call a feature. They can be proposals, they can fit into features. We kind of, squint and see that these can form some subsets of features, but what is a feature is also hard to define and can mean different things for the tools. It can mean different things for the specification. It also means different things from the native perspective when a native application developer is actually looking to port something over. So there are challenges with emulation, and it's not clear if this is actually possible. So we just talked a lot about memory conundrums where performance trade-offs are inherently complex. We have a lot of security-sensitive surfaces when we touch the memory, and historically this has also been true. I think there was one year where Google may have paid more in bug bounties than my salary for that year, but I don't want to talk too much about that. But concurrent mmap and the atomicity of the API calls, or if we decide to port them over into the core specification, are still an unsolved research problem. And generally, when it comes to performance, memory consumption, when it comes to complex applications, has been really hard to nail down. So debugging primitives here are also going to be really helpful. So I know other folks have talked about this here, but security continues to be something that has, I think that's always a priority for us, but especially as we've shipped garbage collection and hash and started an origin trial for JSPI, we've seen a significant increase in the CVEs that we've had over the last 6 months or so, that raises an interesting question in terms of, should we be shipping this many features if what we're doing is increasing the attack surface? We get that feedback from our security team quite a bit. One of the things we're experimenting there with is validation or verification of modules at runtime. The W8 heap sandbox has shipped, which is a relief, because that means that to some extent that can be contained within W8, but that's unfortunately not the case for some of the issues that we've seen with GC and JSPI, which cause type confusion, and then you're out of the sandbox and you've compromised the process anyway. So featureful WASM and making it secure are really quite an interesting challenge. So that's kind of all I have. Thank you for listening to me, and I'm happy to take questions.
Thanks, Deepti. One thing I'm sorry I didn't highlight before the start of your talk is that in addition to all Deepti's work at Google, she was also a chair of the WebAssembly community group, which was our main standards body for a number of years. Okay, yes. With that being said, any questions about the talk? I have a bunch of questions of my own, but I don't want to monopolize your time. Okay, I guess I'll start. So yeah. I was interested that you brought up the memory mapping feature and specifically the concurrent behaviors. Have there been any internal experiments inside Google in other contexts about the kind of concurrent behavior of these things? Because I could imagine even for native apps, this might be something you'd want to push the boundaries on for performance.
Yes and no. I think for native apps, because like I think the challenges are different for native apps. They do push the boundaries, but that's mostly in some defined way because it's very specific to a platform and OS combination. It's just when you step back and you look at it at exposing a portable abstraction, that seems to be much more challenging, where the challenges are slightly different, where in the native application, you want to push the boundaries of the concurrency itself. In this case, we are trying to figure out what is the set of primitives that will allow us to do that. That said, we haven't actually gotten to the point where we're experimenting with concurrency yet. I'd probably have more to say if we were at the point where we've stressed that system more. We're at a very early prototype and we just want someone to use it. Go ahead.
So this is, I guess, like sort of an outsider question. You're talking about the feature detection and emulation detection. What is it that is, I guess, like what layer is like not communicating about what its features are? And is it like a totally impossible thing to
It is not, actually, in my opinion, it is not a totally impossible thing to happen. In the WebAssembly community group's opinion, though, that varies from my own, unfortunately. I think, so at the abstraction, so WASM is portable, right? CPUs know what features they have. We don't want to be able to expose what features CPUs have at too granular level, especially for web runtimes, because fingerprinting is a concern. We want to have like some form of a privacy guarantee that we're able to provide to our users. But there are ways to work around that. Like there's already entropy that's exposed in the current web browsers. There's ways to not exploit that, but at least like, piggyback on that to some extent. For emulation features, when you have a function that is trying to use certain features, the runtime knows what hardware it's running on. So you can establish a baseline to say, if I have AVX on x64 systems, that AVX and above, I wouldn't count it as emulated, but AVX and below, I would count that as emulated. And you could also find that to be different, right? On ARM64, for example, if you had ARM v8.4, for example, which supports more features than the older ARM chipsets, you would have to draw distinctions based on hardware features and performance, and that line is just tricky to find for emulation. So hardware knows about it. VMs know what systems they're running on. WebAssembly doesn't give you the detection primitives, is the short answer.
Okay, thank you.
Recently, me and several others published a proposal for what we called hardware specialized WebAssembly, which I think saw, you had that last slide where it was talking about feature detection and some other things. And specifically in the proposal, the proposal addresses some of those things. We also think it was possible to, for example, solve feature detection. And I just want to, number one, highlight that Michael McLaughlin at CMU had done some work to see how feasible that it was for, I think it was ARM64 or something like that. Have you guys looked at it any further?
No, but I did read Michael's reply, which I think highlights some of the concerns too, where especially if you had the explosion of built-in functions, that's really hard to scale, right? And the runtime is actually implicitly taking a lot of that cost. And the runtime is also at that point in the unfortunate position of being the enforcing authority of what is and isn't a built-in. And I think in some ways there are approaches where I'm okay with circumventing the standards approach, and there are places where I'm not, because I think the standardization framework does give us some guarantee that different people can come and have their needs addressed, whereas I can see browsers really running ahead with that in terms of what they support and what they don't. So with my standards hat on, I don't feel comfortable with that solution because I don't think it sets up the standard for success. I'm happy to talk about this offline too. I know we've talked about it a bunch. Yes, and in February.
Testing. Okay, that's good. We still have a couple of minutes before the remote talk starts. So I have one more question.
Okay.
So I've often found that when Google is bringing a potential feature to the standards body like FP16, often there'll be another part of Google, like a different feudal kingdom within Google, that also realize they would really benefit from this. And I'm kind of interested, is that generally these other teams reaching out to your group asking, how can you make this thing faster? Or are you doing more active solicitation of how can we provide more value to other groups?
So the answer to that is layered. If they have a web application, our team would care about it because we want to make a lot of their things fast. Google is a big company. They have WASM is used in a surprisingly large number of places, and I'm happy to talk to you about that after. So they come to us with a lot of requests in terms of performance, in terms of features. Just given that we're a part of the web platform team, unfortunately, we're not able to do much more than just consult and say, this is how you can do it. This is how we think it might fit, but we're not able to actively work on that, which, again, this is a case of big organizations shipping their organization. So there's, I find that unfortunate, but I think that's kind of how that happens.
Is this on?
Yes.
Good. So, yeah, you were talking about feature detection, but what about different profiles? So I know...
So profiles are a spec construct, and they don't influence feature detection in any way. They're orthogonal, don't solve a problem that implementations have. They solve a problem that the spec has. They don't solve a problem that implementations or tools have.
Right, okay. I mean... But you... I mean, I guess the idea was you detect whether a certain feature is available, and if it is, then you take advantage of it, and if you don't, then you have some sort of workaround to emulate that. But you might kind of give up instead and say, no, I don't want to do that thing.
Yeah, I mean, and I think that you want to be able to do that, but right now you do that in user space. What you want to be able to do is do it natively so that applications don't have to make these decisions at runtime and be prepared for them, and there's no way to do it natively at this time.
Thanks so much. Just to give time for our next speaker, let's thank Deepti one more time. Wonderful. So our next speaker is going to be Frank Emmerich, who is at Edinburgh. I'm speaking in the microphone.
Frank, can you hear us? No, wait. Hi, Frank. Can you hear us? I'm not sure. Can you hear us? We have some. Can you hear us? Okay. Okay, now we are see you. Give me 1 second. Okay, try to speak. Okay, we are not hearing you. Ah, okay. Now try to speak. I think that he can hear us.
Now I can see myself in the stream. That's
Yes.
reassuring.
Can you hear us?
I will get going then. Okay, it's a bit difficult. I'm talking into a void, and I'm not hearing anything from anyone. But I'm hoping that I'm supposed to get going. I'm Frank. I'm also not sure if anyone has given any kind of introduction about me. That's the funny part about speaking into a void. But hi everyone, I'm Frank. I work at the University of Edinburgh. I'm going to speak about the work that I have been doing together with Daniel Hillestrom about implementing the stack switching proposal in Wasm-Time. So as a bit of context, there is a stack switching proposal. There is also a subgroup of the WASM CG working on this proposal. And the idea is to bring non-local control flow to WASM. And you just need to move this window really quick. And the idea is that this way we enable various control flow features in source languages, such as async await, coroutines, lightweight thread generators, first-class continuations, you name it. And the proposal itself kind of originated with something that's based on Plotkin and Prednar's handlers for algebraic effects, which are kind of inherently asymmetric. You have kind of parent-child relationships between continuations. And then there was an Uppsala paper in 2023 about this, about kind of this earlier version of the proposal that we have now. And then later on, the proposal evolved, most notably by adding the switch instruction to it, which is kind of optimized for the use case where you actually want to do something that's more similar to symmetric switching. And I'll talk about the difference between these two things a little bit later. And finally, now, a couple of months ago, the proposal has now moved to stage 2 of the process. And we have two implementations. One of them is the reference interpreter, and the other one is in a fork of Wasm-Time, which is an industrial strength standalone Wasm engine. And we're currently being in the process of upstreaming this, hopefully having a PR open for that this week. So just as a kind of crash course in how the proposal looks like, here's the instruction set. So on the module level, we reuse the tags that were introduced by the exception handling proposal, but we add results types to them. And these tags are basically the delimiters or the effects based on the kind of perspective you have on stack switching. And we add heap types for first-class continuations. And then in terms of the most important instructions of the proposal, we have one to create a continuation from a function reference. And then the next two instructions are basically the ones for the kind of asymmetric switching. So we have one instruction called suspend, where you provide a tag which suspends the currently running continuation and goes back to one of its parents. Or from the kind of effect handler perspective, you're just performing an effect. And then we have an instruction for resuming a continuation, which basically means installing a new effect handler. So we use these tags to denote, oh, on this effect, use this block to handle this effect. And then finally, we have this switch instruction, which allows you to, rather than going to your parent, directly switching to a different continuation. And again, I'm going to speak about this instruction in a bit. So now, kind of as a very simple example, I'm not going to show any code, but just to give you an idea. So here's kind of the hello world of at least the asymmetric use case, which is like a generator. So we have two functions here, the consumer function and the generator function. And the idea is that the generator function runs in a continuation. So what the consumer will do is it will resume it initially. That's kind of the right arrow, which makes the consumer continuation, or maybe it's the main stack, the parent of this continuation running the generator. And then the generator can suspend itself and in the process provide a value back to the consumer. And this way they can kind of go back and forth. The consumer resumes the generator and the generator suspends itself to go back to the consumer. And here you also see this kind of asymmetric nature. The consumer, the parent uses the resume instruction and the other one uses the suspend instruction. And now if you kind of remember the examples I've given on one of the earlier slides, we had all of these kind of use cases like lightweight threads, coroutines, and I'm going to provide an example here with just two functions, task 1 and task 2. And the idea is that they're kind of executing some tasks and we want to switch from task 1 to the other task because task 1 is blocked or something like that. And if we use kind of the techniques that I've described so far, the kind of asymmetric switching, then we would have a situation where you have some kind of stack running a scheduler, which is then the parent of the task 1 that's currently running. And then task 1, if it wants to kind of hand execution over to some other task, it would just suspend itself. And then the scheduler would pick the next continuation to run, in this case, the one that's running task 2, and resume that one. And that would work perfectly fine. The only issue is kind of that our goal was to switch from task 1 to task 2, but we've now actually executed two task switch in the process. So the idea of this switch instruction is that we save one stack switch. So we still have parent-child relationships and we still have these tags to kind of act as delimiters, but we now have the ability to directly go from task 1 to task 2 with just kind of one actual stack switch being executed on the machine. So that's kind of a high-level introduction to the proposal itself that I wanted to give. And what the rest of this talk is going to be about is mostly kind of the journey that we've taken to actually implement this in WASM time, because this was always kind of following this challenge that we had, which is implementing a relatively complex feature in an industrial strength WebAssembly engine with just limited resources. And the limited resource here being people, because in the beginning it was Luna, Phipps Costin, and Daniel working on this, and then later on me and Daniel working on this. But basically only ever two people at the same time, and not really these two people working full-time on it either. And so that's kind of the main constraint here. And the process that kind of we ended up with was the following. And it's not so much that we kind of sat down and came up with this grand plan in some way, but it's kind of over time we figured out that the best way to actually do this and achieve this is these relatively high level steps that I'm then going to provide some details on later. So the idea is to kind of start with a relatively inefficient prototype that focuses on ease of implementation. And then kind of the next two steps, even though I've numbered them 2 and 3, they're kind of happening in parallel. So the idea is to kind of, on one hand, figure out the design where you eventually want to get to for higher performance, and then make incremental changes towards that implementation goal. In particular, no kind of big bang on one day you kind of rewrite your entire application or your entire implementation. But of course, the second step and the third step, they go hand in hand because you may not have figured out how exactly it will look like from day one. So the design will evolve over time. And then finally, in the end, you will hopefully arrive at an optimized implementation. And in our case, the starting point was this kind of relatively inefficient but easy to implement kind of baseline or prototype implementation. And the kind of architecture of WASM time in general is shown here on the right. So the pipeline looks basically like this. We start with your WASM program, and then we translate it to CLIF, which is the intermediate format used by CraneLift. And CraneLift is the compiler that's kind of shipped as part of WASM time. It's supposed to be relatively independent from WASM itself, but it's the compiler used by WASM time in the end. And one important, I'm hearing myself, a bit weird. There's a slight echo in the WhatsApp chat now. I guess I'll have to. So of course the format has call instructions. But one particular way of doing calls is kind of using an infrastructure that's part of WASM-time, which allows you to call into runtime functions shipped part of WASM-time. So you're basically able to cross the boundary between Cliff, kind of trainlift generated code, and Rust precompiled code running in WASM-time itself. Sorry, can we somehow fix this echo that I'm having? Because right now I'm hearing myself in a very loud way, which is a bit irritating. Is it still there? Oh, I think it's gone. Ah, good. Thank you. I will go back to my talk. Here we go. So I was mentioning kind of libcalls, and in a sense they are an escape hatch because they allow you to execute arbitrary Rust code by calling into them from the CraneLift generated code. And we've used them very liberally in the kind of initial version of what we've written. Because most importantly, we've used them to perform the actual stack switching by calling into an existing library called WASM-time Fiber. I'm going to talk about a bit more of that in a moment. So the actual stack switching happened this way. And then also to perform allocation, and it was the case a couple of times that we would simplify the implementation work this way. So basically, whenever something was difficult to do, rather than emitting the right Cliff code, we would just implement it in Rust first and then call into that. And now some details on WASM-time Fiber, this library that we used. It's a general-purpose stack switching library that's developed as part of WASM-time, mostly because there is already an feature for asynchronous computation in WASM-time, but that's not kind of integrated into the core language. So that's basically from the embedder side. So that's not what our proposal is about, but it meant that this library was there for us to use. And based on the platform, what you have at the heart of this library is basically handwritten assembly, which does the things that you would expect from a function or from functionality that does stack switching. So basically, save your registers, adapt your stack pointer, and then jump somewhere else. And here on the right, we kind of see the high-level stack layout that this uses. So in my examples, stacks will grow down. So at the very top, and this stack here is suspended right now. So at the very, very top, we have the stack pointer where we left off, in a kind of reserved area at the very top. And then below that, we have the regular stack frames. Then we have caller save registers because we actually, this switching function is a function, so we called it like a function. And then we have the stuff that this handwritten assembly function itself saves, like the instruction pointer, frame pointer, and the call save registers. So that's what the WASM-time Fiber library does. Now I want to talk about the architecture that we wanted to get to eventually. And the main goal here was that eventually we wanted to perform the actual stack switching itself from code that's generated by CraneLift rather than using libcalls for that. And in particular, we want to get rid of basically all the libcalls except the one for continue, because that needs to perform allocation, so it would probably always have to need to happen in the runtime. So the idea was that we would add a new Cliff instruction that would then compile to the right kind of basically what the old WASM-time Fiber switch or something similar to what this was doing in the past. And the kind of the guidelines here for us was that this was supposed to be like the minimal addition to CraneLift that we needed to do this kind of thing, and for it to be platform independent. And now here in this little speech bubble, instead of a call that we compile now, the idea is to directly compile to this Cliff instruction, our WebAssembly. And now we see some details about this instruction. So the idea is that it acts, instead of kind of being given the data that it needs to act on, like the new instruction pointer and the new stack pointer, we're not giving that directly to the instruction, but in order to be platform independent, we give it basically pointers to memory where it will find that data, and also a pointer to where it's supposed to write the current state. And then we have the ability to pass around some payload. And we call these areas that it acts on control context, and the actual layout is platform dependent, but it will contain something like your stack pointer, your instruction pointer, stuff like that. And interestingly, it's actually providing symmetric switching. So at the even though the proposal as a whole is based on asymmetric switching, this core primitive that we needed to add to the compiler is actually doing symmetric switching. And here on the right, we see that the stack layout that this instruction uses is actually quite similar to what we saw with resin-time fiber. So now at the top of the stack, this kind of reserved area, we have the control context, which contains a bit more now, not just the saved stack pointer anymore. But for example, it contains the pointer down to the end of the stack still. Then we have the regular stack frames of the stack that we're running in this continuation. And in the end, we have the saved registers. So basically all of the data registers down here, and up in the control context, we have like the kind of control registers in a sense. And if you compare these two, they are relatively similar, and that's not a coincidence. So we were quite interested in making this happen and kind of to ease the transition. But it turned out that actually with the constraints we had, it was kind of, this was a natural pick. So we didn't kind of push ourselves into a corner by choosing a layout that's kind of deliberately similar to the old layout that resin-time fiber used, but it actually turned out that the similar layout was a good choice anyway. And actually what I'm not showing here is that we even had a third layout, which is kind of in between the two, that made the transition even easier, so that one day we could just flip a switch and go from resin-time fiber, or rather our own forked version of resin-time fiber, to the new stack switching instruction. And here are some benchmarking results. This is basically just testing the performance difference at the one commit where we kind of flip the switch. And these are all micro benchmarks, so take them with a big grain of salt. But still, if you look at this very last line here, that's basically a micro benchmark that just does suspend and resume instructions in a hot loop for like 1 billion iterations. And here we're seeing like a 6x performance improvement. And of course, that's great. We're happy with that. But that's actually like surprisingly good. Like the lib calls have some overhead, but we wouldn't necessarily expect that to be like a 6x factor. And I'm running out of time, which is why I have an analysis of why this is happening. There's actually something really interestingly on the CPU architecture level happening here, but the TLDR is that function returns and stack switching really don't like each other. They confuse the CPU's prediction unit for returns, which means that at every stack switch we had consistently had 4 mispredicts in a row, and that's actually where this big performance difference came from. If you're curious about the details, then talk to me. And now I want to kind of go back to these 4 steps that I mentioned earlier and kind of reiterate what that exactly meant for us. So I said the first step is kind of to start with this inefficient but easy to implement prototype, which in our case we built on existing mechanisms, which on one hand was this resin-time fiber library and the libcall mechanism. And in particular, and this was kind of a shallow implementation. We didn't have the touch train lift at all at this stage, which was very good because like none of the people who worked on this had ever touched resin-time or crane lift before. So kind of reducing the surface area that we needed to touch for the initial prototype was like a huge help. And then for every time something was very complicated, we just used libcalls in the initial version. And then to kind of sketch a design for the more optimized implementation in parallel to the other orthogonal implementation work, I worked on a prototype for how the stack switching and crane lift should actually look like. And then over time, we kind of adapted our own copy of resin-time fiber to incrementally move in that direction until we eventually switched to the actual stack switch instruction. And of course, what I haven't really gone into today is all of the other small improvements that were not directly related to the stack switching itself, but things like payload passing and allocations and stuff like that. But of course, there were a lot of other things that had to happen along the way. And then 4th step ideally is you arrive at an optimized implementation. And as I said, we're currently kind of applying the finishing touches to OPR to actually upstream this. And here are some resources if you're curious. And other than that, I think it's question time.
Frank, hello, are you able to hear us?
Yes, I am.
Great.
This is a nice change to the last 20 minutes.
Okay, we may have to do some toggling to make sure you're not hearing your own echo, but we'll just try and make that work. So, do we have any questions for Frank? One at the back.
Hello. I hope you can hear me.
I can, yes.
Yeah. So I was comments as a question, but I was actually surprised when you said almost like on stack switch because it confuses the return predictor. I was wondering if you have any more information on that, if something.
You're currently kind of like always like the audio is on and going on and off. It's really hard to hear you.
Okay, let me
All
try
I
again.
heard
Maybe
is
I
that
just
you're
didn't
curious about
hold the
the
mic close
return.
enough. Is this better?
Oh yes, now it's better.
Yeah,
Now it's
yeah,
better,
yeah.
yes.
So I think you briefly mentioned you had multiple mispredicts for each stack switch, and I was kind of surprised because at least that's not my mental model of how the CPU works. I'm wondering if you have any more information on it because I'm kind of curious what's happening under
Yes.
the hood. Yeah.
So this is not because of stack switching in general, but the reason is that we always had 4 nested calls, and the 4th nested call would do the actual stack switch, and then you would go to another stack where you would have to return from 4 different functions. And these 4 different functions were all So the problem was mostly we had these 4 nested functions on each stack, and we switched and then returned from 4 different functions, and this is what confused the return address prediction terribly, because the return address prediction expects whenever you return, right, the return address will be the address of the last call. It tries to match them together, but this isn't true anymore in the stack switching scenario, where you're basically popping stack frames on one stack, then you're going to another stack, and then you're popping frames, but they're not the frames you've just added. They are different frames, and that just confuses the CPU, if that makes sense.
Yeah, I think that did. Thank you so much.
So this is a very related question, but I'm curious if you have any hardware that supports modern shadow stack instructions. If you have any thoughts on performance with shadow stacks, which I imagine may improve your mispredict situation, but also will mean you need a kernel context switch in some cases on Intel, I think. So just curious if you have any thoughts on that topic.
To be honest, it's not something we have looked at at this stage. It's definitely like something we want to think about, but we haven't done so at this stage.
Great, I think that's a natural place for us to end the questions. Let's all thank Frank one last time.
Bye, everyone.
I hope you're able to hear the applause there. Thank you for talking.
No, but I imagined it.
Okay, so our final talk for this session is Yaolun. Okay, thank you so much. So yes, our last talk is going to be Liang Yaolun, who is an intern at Edinburgh University right now, who has just finished up a wonderful internship at Edinburgh University, and you're going to be talking to us about stack switching in WASM SpecTech. Please take it away.
The new extension, as many has mentioned before in this workshop, that's the stack switching extension. And I'm implementing the extension in SpecTech, which has some interesting technical challenges, which I will show. Okay, so today's talk will consist of, well, some background, and I'll show the way that I implemented in SpecTech now, that is a bubbling semantics, and I'll show some of my thoughts and some of proposals to implement native context in SpecTech. And finally, I'll briefly introduce some other changes to SpecTech that is necessary to make the implementation working. Okay, so first, let's have a brief introduction of how formal WebAssembly semantics is. So for example, consider the expression 1 plus 2 times 3, which is really simple. And in WebAssembly, it's written as I say to the multiply and add 1, 2, and 3, which is great. And actually, as WebAssembly is a stack language, the stack is written as this. It's 1, 2, plus, and 3, and multiply. So it steps to 3, 3, multiply, and steps to 9. And actually, in specification, it's written as 2 rules. So the first rule is we have a C1 and C2, and we have a binary operation. And we goes to C if C is a possible outcome of the binary operation on C1 and C2. That's the first rule. And the second rule is if C1 and C2 has no possible outcomes, for example, it's a division by 0, then it traps. Okay. So actually, there are 2 versions of the specification. The version shown above is what we call the prose semantics, and we also call that algorithmic semantics. And the version below, we call that declarative semantics. An important difference of the 2 semantics is that the prose semantics or the algorithmic semantics has an implicit instruction sequence, while the declarative semantics has an explicit instruction sequence. So as we can see, the prose semantics has, well, an assert, 2 pops, and an if branch. And so, for example, the if branch here corresponds to the first rule on below, on the declarative version. So if it is defined, then return some possible outcome. If it is not defined, then trap. So as we can see, each instruction in WebAssembly has an algorithm in the algorithmic version of the specification, but it can have multiple rules in the declarative version. Okay, and let's turn to SpecTech. SpecTech is a tooling that allows us to write the declarative version of the specification in text. So, and then we can translate the text specification to both the declarative version and the algorithmic version automatically. So this is work by Dungeon and many other people. presented in PLDI 2024. So the way the spec works is that the spec DSL that I shown before, this DSL, is first passed to an we call it external language EL, which is basically the same as DSL but as a tree, and then it is elaborated into the internal language, the IL, which is still basically the same modular elaboration. And the interesting part is the IL to AL translation, which translates the declarative semantics to algorithmic one. And then from the AL, we get the pro semantics, and oh, sorry, it's a bit blurry. And then from the AL, we also derive an interpreter that automatically interprets WebAssembly from the specification given. Time is not. I'll skip that. Okay, so to introduce stack switching, we need to know frames in WebAssembly. So frames are the WebAssembly concept to implement control structures at runtime. So for example, consider the block and branch instructions. So the branch one here means branch out 2 blocks and skip to the second innermost block. So the branch one here will proceed to C directly, skipping over A and B. Okay, let's consolidate a bit. So, in the stack, it is like this. The rows of the blocks and the branches are on the above. So, to execute the 2 blocks, we first translate the block, transform the block into a label, which is a frame, which we call it a frame. So, and the outer block is translated into a label. The inner block is also translated into a label. Then the branch instruction get bubbled out. So the branch 1 get escaped from the innermost label, which becomes a branch 0. And then since a branch 0, it escapes the label and brings out the returning value, which is either to got the const 0 and skips to C. So label is a kind of frames, and there are other kinds of frames for exception handling and for function calls. And these frames are what we call administrative instructions, which are instructions that present only at runtime, but not at in the source level. And it is only present on runtime for the declarative semantics. Okay. And with the background of frame, we can finally introduce the semantics of stack switching. So stack switching, well, is switching stacks, right? So there's a continuation part in the WebAssembly store that contains a lot of possible continuations that we can resume. So when we execute resume, we introduce a prompt frame, which is a temporary name by the way, and move the stack into the, so we move the continuation from the store into the actual stack. So let's see, as you can see, the red box is moved into the stack. Oops. And this is the resume process. And for suspend, we have the reverse process. So first we have a suspended marker, and we move the stack outside the real stack into a temporary area. We replace the suspend instruction with a hole because we do not need the instruction anymore, and put it into a continuation area. And since we are handling the tag here with the label, we replace the prompt instruction with a branch to the label with a reference to the continuation. So that is basically what stack switching is doing. The way that I implement stack switching is a way that I call a bubbling semantics. So the bubbling semantics is just like the semantics of the branch instruction that I introduced before. So the branch instruction is escaped from the innermost frame all the way out to the outermost frame that it needs to escape, one by one. So it's bubbling. But the original proposal defined the semantics in a different way, which is defined in context. Context is not a new concept in a WebAssembly specification. It is used to define a lot of things. For example, also the branch instruction. So for the branch instruction, we have the block context, which is basically a hole surrounded by, so it can be a hole, or it can be a context surrounded by a stack and a sequence of instructions, or it could be a context surrounded by a frame, a handler frame on a prompt frame. So with context, we can simply, specify the semantics of the branch instruction as, well, to branch out L blocks, we can just branch out L as the count of the label frames. So the superscript here means the number of label frames to escape. So as you can see, I've made a typo here. It should be K here, not K plus 1. So the K here means the number of labels to escape. But without context, we have to write every kind of frame one by one in separate rows. And this have to be repeated for every instruction that needs to escape these kind of frames. So that's not very good. Contexts are also used extensively in stack switching. This is a context I use in stack switching, which is really similar to the block context. But one important difference is that this is the semantics of the suspend instruction. So as you can see, when we match a handler context, we need to, after we match it, we need to store it into the store. So in the specification, we store the context directly in the store as a component of the continuation. So we need to reify the context, probably not as a tree. So my implementation was to make the context a list of frames. So for example, consider the instruction sequence below. We have a stack of values, we have a frame, and we have an instruction sequence at the end. So the context is defined as, well, the red part is the first frame and the blue part is the second frame. Well, which is basically what is the context. So in my implementation, context is a list of frames. You can definitely also define it as a tree, but being a list makes it easier for the implementation. Okay, it's my implementation now, but it's really kind of ugly because you have to write a lot of repeated code here. So you see, we have a lot of repeated rules, but with context, we can write these rules in one rule. So we're thinking about introducing native context into SpecTech. So in SpecTech, we can just write contexts instead of writing bubbling semantics. So to recap, the architecture of SpecTech is like this. So the important part is the IL to AL translation, or we call the animation pass. But the internal language is the declarative version of the semantics. So it operates on a sequence of instructions. So the design that we are pursuing now is to have a variant of the internal language without context that is only for the IL backends, the theorem provers, and a future potential IL interpreter. And another translation directly from the IL with the context to the algorithmic language, which is without primitive context. So we have two transformations that remove context from the language. One is the IL to IL pass, and one is the IL to AL pass. We do that because the execution model of the IL and AL makes it pointless to use the same transformation for the sugaring of contexts. So, and for the IL backends, some might claim that supporting context natively for the backends, especially the theorem prover backends, will pose a challenge for the backend. So we might want context to be processed before the code enters the other backends. So we want an IL variant without context. And the design that I'm currently pursuing is to generate a match function for each use side of the context. So for example, we consider the block frame that we've mentioned before. Oh, sorry, is k not k plus 1. So this is the rule of the branch instruction, right? So ignore the colors for a bit. So what this does is, or what we need to do is, when we meet a branch instruction, we count the number of blocks to escape, which is L here. And we match L blocks out, and well, L labels out, labels as a frame, and then match the L plus 1's label, and then consider the number of values to capture, and then capture n values here. Oh, yeah, the k must be equal to L. Yeah, okay. So that's what's happening actually in the implementations, but in the IL sense, what's happening is we are matching these instructions with this pattern. With this pattern. So we're matching a pattern with n values and a branch with I don't know how many blocks. So the blue ones here are the outcomes of the match function, and the red ones are the inputs. Sorry. What's happening? Okay. So the match function should be like something like this, this is a type signature. So we receive a number of values to capture, and we receive the instruction sequence to match, which is the red box here. And we return the number of labels, which is the k here, the context itself, the values that are captured, and the number of branch, and the index or the parameter of the branch instruction. So in this way, we can capture, or to say, we can match a pattern and not a concrete instruction here. So I'll declare that a context is a ADT plus a match function. well, time's up. So, but there are other changes to SpecTech that are necessary, which I will skip. To summarize, I've implemented the stack switching proposal in SpecTech, and there are some changes that needed to make an implementation work. There's a possible design for native context. And the takeaways are, so having context in SpecTech is quite beneficial. And automatically transforming declarative semantics to algorithmic is hard. And automatically transforming context to bubbling is also hard. And the SpecTech implementation is designed to work with current spec, not work with future extensions. So it might need extensions for future proposals, and it is fragile. But anyway, try SpecTech for your future proposal. Thank you.
Thanks so much. Any questions? So I imagine that with the approach of generating extraction functions from the context definitions, when you turn that into the interpreter or the prose semantics, do those extraction functions show up in the semantics at that point? Or do you try and handle them a different way?
No, we handle that in a different way as in this picture. So the transformation in the next slide, these transformations are only for the IO to IO pass, not for the IO to AL animation pass.
So if you do have a context in the rule and you want to animate that, do you need to do something special if you don't have the extraction function to make it work?
I think there's no general way to do that. So I implemented in a rather ad hoc way. So a bunch of heuristic and pattern matching.
I can ask a second question. Do you think evaluation contexts are going to get even more complicated in future?
Yes, I think with the introduction of more frames, we already have exception handling, we have effect handlers or stack switching, and there should be more frames in the future as more control structures.
Well, the one I was immediately thinking of was concurrency, potentially.
Yeah.
Cool. I think that's great. Let's thank Yaolun one last time.
Thank you.
Okay, so with that, we have reached the end of our third session. We have one more session still to go. It's a half-hour break now. We will be back at 4 p.m. local time. If one thing I would like to flag up, if anyone would like to give a very short impromptu talk at the end of the next session, we do have a section for lightning talks that are roughly 3 minutes long. We have a few sign-ups now, but they've not filled the whole time, so if anyone would like to propose something at the last minute, I'm all ears. Come and talk to me, or fill in the Google Drive up until the end of the next break. See you in half an hour.
Okay, now, okay, yes. Yes.
Elliot, are you able to hear me?
Yes, just barely, but I hear you.
Great. I'm going to open the session and then we'll just get started with you in a second, okay? Okay, hello
Okay,
everyone.
great.
Welcome to the final session of the WebAssembly workshop. Thank you for bearing with us. Our first talk is going to be Elliot Moss talking about simple transactions for WASM. Elliot, please take it away.
All right, thank you very much. And I thank the organizers for allowing me to present remotely. It wasn't practical for me to be there in person. I wish I could be with you. So let me just dive right in after mentioning my co-partners in crime here. Tony Hosking and Steve Blackburn are my more senior associates in this project, and Hal Shu and Angela Upreti are graduate students working on it. So let me give a little bit of context. Our overall goal and reason for being interested in transactions for WebAssembly is that we're interested ultimately in persistence for managed languages using non-volatile memory, perhaps of various different kinds. The more recent byte addressable non-volatile memory is of interest, but we would like things we do to work on other persistence platforms. Now, we believe in persistence by reachability for managed languages. That makes the most sense so that objects don't, disappear from your object graph just because of persistence or a failure. And this ultimately also argues for some kind of atomic transactions, ACID transactions for a persistent system so that you have clear units of work against this persistent object graph. In general, one wants to support multiple threads that act concurrently, and we would want this to be portable across a range of target systems. Also would want it to be easy to target from compilers to encourage research and development of persistent programming languages. And we'd like our platform to be neutral as to the source language to make it easy to target. Now, this is a research project, but it could move to production ultimately. But our goal right now is to enable exploration, but also to admit efficient implementation, including a range of optimizations. So why WebAssembly as a target? Well, we can build on the WebAssembly GC extension to support persistence by reachability for those who prefer a more linear memory semantics. We can also support persistence in the WebAssembly linear memory. We can interoperate with, but do not require, there be WebAssembly threads. And we want a relatively simple extension. So we call this the simple transactions extension, avoiding fancier things like nested transactions. So the persistence would build on this simple transactions extension as a further extension. The value to that is that persistence then would be optional. Now, why WebAssembly? Well, we can tie in with existing implementations of WebAssembly. And so there's mature design and an active community as opposed to some more narrowly adopted or more narrowly known platform. And the extension itself is comparatively modest semantically. I think about the minimal needed to achieve transactions. And we intend to make this design and the prototype available to the broader community. One reason this fits with WebAssembly, if we think of WebAssembly as having a general goal of abstracting underlying hardware resources, this fits with abstracting non-volatile memory of one form or another. So our approach to simple transactions. So we create or add new transactional versions of the more stateful parts of WebAssembly. So for example, for the garbage collected objects, structs, and arrays, we add transactional structs and transactional arrays, and we just prepend a T for those types. We add global variables. They are ultimately could also be roots for persistence. And we add transactional linear memories. Now, all of these add to the existing parts. The existing globals, memories, and so forth would still be there, though we don't suggest mixing the two most of the time. And the idea is then a single engine could support non-transactional work with existing WebAssembly modules, but could also support transactional work. Now, this implies, we believe, additional types. We want to segregate transactional and non-transactional data according to type. And we split out the opcodes as well, though that's not absolutely necessary. We mostly add this, if you're interested, at the binary level through opcode and type prefixes. Now, using separate types avoids potentially costly dynamic checks if we just dynamically distinguished between, say, arrays and transactional arrays. The runtime would have to be checking which kind it has all the time, but we can leverage types to avoid that sort of dynamic check. Now, the clear separation of transactional and non-transactional data avoids the messes you get into if you try to mix, for example, transactional and non-transactional data within a transaction. You know, what happens if the transaction gets partway through and has to stop and unwind? What happens to the non-transactional data and so forth? What happens to non-transactional data if you have concurrent transactions and so forth? So we propose to keep the semantics simple and separate them. But the engine would support both kinds of data, but you probably wouldn't mix them that much in a single program. So what semantics do we propose? So the ACID semantics, but without the durability, that's what the persistence extension beyond this would add. And we define conflict between transactions as occurring when two transactions access the same data and at least one of them is modifying it. Now, the conflict part of this could be dropped if you have a strictly single-threaded environment. But transactions can still be useful because they support all or nothing, that is rollback or undo and then possible retry of an action. Now, what is the scope of a transaction? Well, we add transactional functions and transactional blocks, which can begin a transaction. Now, since we're not supporting nested transactions, if you have, say, a T block within a T func, the T block itself doesn't add anything, or a T block within a T block, and so forth. Or if a T func calls a T func, likewise, you're not entering a new transaction. But this gives a clear separation known statically just from inspecting the code between transactional and non-transactional execution. So transactional operations are allowed only in transactional scope, and non-transactional code, though, is allowed to contain a transactional block, which starts and runs a transaction, or a call to a transactional function. Non-transactional operations are allowed only in non-transactional scope. Now, we do have a slight exception to these two rules. Immutable data can be accessed from any scope. That's perfectly safe. The data can't be changed, so there's no problem accessing it. Now, just to give a quick example, what about accessing transactional linear memory? What would that look like? So every load and store opcode has a corresponding transactional load and transactional store opcode. Now, I note, again, we could simply reinterpret load and store in transactional contexts, because those contexts are statically known, and the validator or loader could translate those to a different internal instruction to avoid dynamic checks. The present scheme, it gives a little more of a cross-check of intent, but could be dropped if that's deemed a better way to go in the long run. Now, conflict and undo are defined in terms of some granularity. You could have a granularity of a single byte, but there'd be a lot of overhead of the metadata for tracking the use of individual granules by transactions. So a larger granule makes more sense. So it's likely a power of 2 in the linear memory. Think, roughly a cache line, so somewhere, between, say, 32 or 256 bytes might make sense, depending on the size and other cost of the metadata. Each T global would be a separate granule, most likely. And then tables and other things also act transactionally and might need a granule chosen for them. Now, these granules form part of what's known as the transaction's read and write sets, which track dynamically as the transaction executes which things it is read and which it is written so that you can derive the conflicts. For written things, it would also track, if we're doing an undo style transaction semantics, it would track the original value of the granule so that if the transaction fails, that original value can be restored. And these granules, in the linear memory anyway, need to get checked on every access. Now, what about the heap, though? Now there, what we did was to add to reference types an access permission. There could be none, which says we haven't accessed this or we don't know that we have access within this transaction. But we can gain read or even write access to the target object within a transaction. So we add 2 cast operators to support gaining the access, and this is what does the checking of, does this transaction have access to this granule yet? And if not, it tries to gain that access. So these are called tref.castRead and tref.castWrite. Now, this permission is only part of the type. It's not part of the reference value. So we're leveraging the type system, but the values don't have any overhead here. An important thing to note is it would not make sense to store the permissions, because once something is stored in the heap, then someone else could load it and believe they have access to the target object, but they need to check it in the context of their transaction. Now, using the types this way allows us to optimize away a lot of checks. So if I, for example, in a given function, read an object, same object multiple times, and it's apparent that it is the same object, then we can do the cast once and proceed to use the object without doing further checks. Now, this all implies that the object is a unit of granularity in this design for both conflicts and undo. Now, if doing this on a whole array is a problem, the solution would be to break the array into subarrays, or arraylets, it's sometimes called. So let's look at an example. Let's look at some actual code. So we have a module where we're going to declare, allocate, and access a transactional struct type. So here we define the struct, and the new construct is tstruct. And this struct is going to have 2 fields, I, a 32-bit integer, and f, a 64-bit float. Then we have a transactional function that takes 1 integer parameter, 1 float 64 parameter, and it's going to return a reference to a transactional struct. And what it's going to do is create a new transactional struct. And this is all fine, and in fact, this particular function can't really cause a conflict because it's only creating and accessing a new transactional object. But should always succeed, provided allocation is fine. Now, if we want to access that, we might say wish to read the integer out. So we indicate that we have a tref parameter, and we can do a tstruct get, provided we do a tref cast read on the object, on the reference first. And then likewise for writing. Now, one could put the burden of doing the check into the caller and add this type annotation into the parameter type, and then you would not need a cast inside the function. So that's the kind of transformation and optimization that one can perform because of the way we have put the permissions into the types. There we go. Now, again, a review of the overall rationale. We believe simple flat transactions offer users the most functionality with the least implementation and semantic burden of understanding. Segregating the types and the transactional state, transactional and non-transactional, helps keep the semantics simple and clear. And you could, end up with double or missing updates, non-serializable behavior, all kinds of nasty things if you allow mixture. And you can access transactional state from a non-transactional context using a short transactional block. And of course, there is overhead to that, but it does keep the semantics clear. We believe the transactional reference access permissions that we added help reduce overheads. We also believe that leaving persistence to a separate extension is a useful optionality. Conflicts and undo were easy to specify in terms of granules. And this overall seems to integrate well with other extensions we're aware of. What is our status of design and implementation? We cloned the WebAssembly GC proposal specification and wrote our draft specification as a modification or extension to that. We have a complete OCaml reference implementation by extending the existing one for the GC extension. We have tests of most of the features available and passing on that reference implementation. We're writing more tests. We have a more performant implementation in Ben Titzler's Wizard WebAssembly engine. That's in progress. In fact, it's mostly there with all the opcodes implemented in both his straightforward bytecode interpreter, but also the faster interpreters that include some JIT support. We just need a more complete transactional runtime for this, and that's actively being worked on. We also are in process of a WebAssembly to WebAssembly optimizer to do some of those transformations to remove redundant access checks and other transaction-related improvements. Now, slightly more in the process of design rather than implementation yet is persistent transactional Virgil. Since we're working in this Virgil environment, that's a natural language to extend. It seems to us to be in a good place of a rich enough language to be interesting, but one whose implementation is still simple enough to be a reasonable project for us to extend. And yet the implementations and optimizer and so forth are reasonable, though not production level like, say, GCC. Right, and so we have a WebAssembly GC extension target backend for Virgil underway. And that concludes my presentation, and I'm happy to take questions.
Thanks so much, Elliot. I'm not sure if you heard the applause there.
No, I didn't. The volume's a little low.
Believe me, they were loud. Anyway, who has questions? One here.
Thank you for the talk, and I could understand that we could define transactions on WASM and also undo them if necessary, but I wasn't quite sure when we undo transactions. So is it integrated with, for example, exception handling proposals? So when exception is raised, it is undone, or is there anything else that triggers?
Yeah, so that's a great question. So undo and such happens, I guess, in at least two circumstances. One would be if you encounter a conflict at runtime, and that's unpredictable. And so it can kind of happen at any point. There's not really any great way to handle it beyond undoing and possibly retrying the transaction. Another possibility is you're running along trying to do something, encounter a situation where you can't continue. You think of, your typical business sort of thing. You've started to arrange something for someone, they present their credit card, and then it's declined, so you have to back out of some of the work you're doing or whatever. So that would be a more programmatical end of transaction. Yes, this can integrate with the exception handling mechanism. So in the semantics that we've implemented, we model the failure as a special kind of exception, and then there's an additional kind of handler. So if there's a runtime generated undo, then that's something where you get presented very little information, a small integer code. Imagine if you wanted to allow hardware transactional memory as a best effort first try for transactions. All you get out of that is a very simple code. But we also have in mind that if users throw a transaction, they might be able to throw it in a mode saying, I want this to end the transaction, or I want this to be viewed as a proper termination of the transaction, but where the exception propagates outward to a caller. So it has to do with whether you're winding the state back or keeping it, which is somewhat separate from whether you're throwing an exception coming out of the transaction. Does that help?
Yeah, sure. Thank you.
Thanks so much. I think we have time for one more question, and at the same time, could our next speaker get onto the podium?
In the WASM to WASM optimizer, could you speak more to what other transaction-related improvements you've made? I'm sorry if you've already mentioned it and I missed it.
Oh, no, I didn't get into much detail there, but thank you for the question. So the thing I mentioned more directly in the talk was the kind of obvious thing of avoiding clearly redundant checks, which is a kind of redundant operation removal. One can also do that speculatively, like you might have an object that you're definitely going to read, but maybe going to write. And then depending on the statistics, you might say, well, let's go ahead and do the cast write first. So there are speculative optimizations like that. But beyond that, there can be things like if you have a number of short transactions, you might choose to group them together into one larger transaction. So that's a somewhat more advanced kind of transaction transformation.
Thank you.
Yeah, thank you for the question.
Great, thanks so much. Let's all thank Elliot one last time. Thank you, Elliot. We're going to switch to the next speaker now.
Okay, thank you.
All right, so our final timetabled speaker before we move into the lightning talks and the closing discussion is Guanan Wei. Please take it away.
As we all know, WebAssembly is a stack-based low-level IR, and it's pretty fast, and it's already supported by all those major browsers. And one nice thing of WebAssembly is that it offers official specifications from its beginning, and it has reduction semantics for the dynamic semantics, and also static type systems, and constraining the shape of the stack. And also those meta-theory result also follows from the formalization. And another nice thing is that there are a lot of ongoing work and new features adding to WebAssembly. For example, effect handlers or stack switching, which has been mentioned multiple times in today's workshop. But let's take a closer look of the reduction semantics. And it's basically specified as a transition between configurations. And each configuration has a global store S here.
and also a list of values, which are those values for local variables, and also a sequence of instructions. And we can substitute the translation for that. An example here shows is how loop works roughly. And we have a loop and has the body of the loop. And when we go into the loop body, we will kind of copy the body of the loop and using an additional administrative instruction called label here, which stores what the loop body is. And later when we have a branching instruction inside of the loop body, we're going through to search what the corresponding label to jump back to. And then we expand the syntactic structure along the transition of the configuration. And this is explicit by two-modal evaluation context. It's also quite verbose. And this duplication about the syntactic structure and searching through the stack, it's causes a lot of inefficiency if you implement naively, especially for deeply nested frames or labels. And more importantly, the style of semantics defining as small step reductions is not compositional and also not tail recursive. So because it's not tail compositional, originally we want to do something like partial evaluation or program transformation. This has become a bit tricky or not ideal to deal with. And also because it's not tail recursive, if you want to implement this style semantics in a function language, it's not ideal for performance or space consumption as well. So alternatively, we look at the semantics of WebAssembly, and we want to reconstruct a semantics using continuation passing style, which means instead of using first order representation for the control construct, we can use continuation function in the meta language to represent the control structures or control semantics. And what we eventually have is a compositional and tail recursive semantics for a subset of WebAssembly in continuation passing style. This semantics can be implemented as an interpreter pretty much straightforwardly, as a big step interpreter, or you can also view this semantics as a transformation from WebAssembly to lambda calculus. Now, before going into the details of semantics, I just want to quickly going through a subset of WebAssembly where we have labels, identifiers are both natural numbers, and those ordinary data types. And for instructions, we have those instructions manipulating the stack. We have instructions to get and set local variables, instructions for structured control flow, the block, loop, and conditionals. We also have branching, function call, and return. And the function body basically containing a list of instructions, and the top level of a module is just a list of functions. Okay. And what we really want to do is to define such a semantic function, the semantic brackets, that maps a list of instructions to another function. And here I showed the signature here. The semantic brackets takes a list of instruction and producing another function. And this another function takes a stack, which is a list of values or represented by a list of values, and also an environment. And this environment is really just, we use it for local variables. And additionally, it takes a continuation. And this continuation is a function that taking the current stack and also environment, producing the answer type. And we explicitly leave this answer type abstract so that user can customize a little bit. So far, this is really all standard, right? Nothing really special. It's just a CPS interpreter. But what's really new here is that we need to add additional trial component to the interpreter, which is a list of continuation, or we use it as a stack of continuation, which we will go into details to see how we provide such values and use those values. And because our semantic function takes a list of instructions, we were just going through all possible choices here. And the first one is that the list of instruction is really just an empty list. And in this case, we have finished the current computation. And the natural choice is really just to call the continuation, which is a kappa here. And but later we will see how this comma coming from. But this is a simple case when the list is empty, okay? And the next group of instruction is really just manipulating the stack. For this no op, we just recursively applying the semantic function on the rest of the instructions, right? And for the constant instruction, we just get the constant C value C and push it on the stack, and then recursively calling the rest. And for add, we assume we look at the stack, and there's already a value V1, V2 on the stack. We add the result, and then calling the semantic function on the rest of the instructions, right? And similarly for local variables, get and set, we just access the variables from the row, for get, and for the set, we just update the environment role with the corresponding value retrieved from the stack. Okay, so far this is really all simple, straightforward stuff, and we haven't really used the continuation or the trial neither. Then we look at the semantics for block and branching or break. And here the block takes additional annotation about the type, which takes the input type, the input arguments and output arguments on the stack for the block. And the block body is this ES, which is a list of instructions, right? And how should we define the semantics for that? Before going into the formalization, let's look at informally how those things work. And the first thing is that those blocks, they are structured and they can be nested. Here on the right here, I showed example here, we have a block, and inside the block, we have another block, right? And important thing here for the block is that a block has a label. And this label can be either named, like L1, L2 here, or just the nameless as the Brown indices. And more importantly, those labels, they serve as a branch target. So inside of a block, we can have this BR instruction that referring to that label introduced by the block, meaning that we want to jump to that somewhere introduced by the block. And for the block semantics, we're really just jumping to the end of the block, right? So the idea here is that we need to remember the escaping continuation once we are going into the block, so that if there's a BR instruction inside the block, we can just discard the rest of the continuation and jump to that. Okay. Then into the definition here, we're really just defining the kappa 1 as this escaping continuation by which recursively calls on the rest of the instruction. And this is just a recursive call on rest. And the important thing here is that this kappa 1 is used as both the ordinary continuation and also appended on top of the trail. And then at the later point, if there's a BR instruction inside of this block, we'll just use a corresponding label to retrieve that continuation from this trail and just invoke it, okay? So the next thing is we want to look at loops. And similar to blocks, loops also introduce a label as jump target, but different from blocks, those branching targets introduced by loop will jump back to the beginning of the loop. This is different from those jump target introduced by the block. And here, the example shows we have a loop L1, and inside of the loop body, we have a nested block, L1, L2, and there are branching instructions jumping back to L1 here. And if there's no branching happens, then the loop finishes. We're just going through the next instruction right after the loop, okay? Then the idea here is we need to have two different kinds of continuation. One is just following through to the immediate next instruction, and the other one is to going back to the loop. So this idea can be also expressed straightforwardly in our formalization, where we define first this kappa 1 is the just following through continuation, capturing the rest instruction of the loop, and also there's a kappa 2, and kappa 2 is both the body of the loop and also the branching continuation for this loop. And note that this kappa 2 is defined as a fixed point or recursive function, so that inside of the definition of kappa 2, we're appending kappa 2 onto the trail as well, so that later if there's a BR instruction inside of the loop, it will goes back to the original point of the loop here. Okay. Then we look at function calls, and it's kind of similar to blocks, but we need to retrieve the function body. We just use this auxiliary function lookup function to get the function body. And there's also this build environment to construct an environment containing argument for this function. We define this kappa 1, which is a continuation for this function call, meaning that we're recursively applying the semantic brackets on the rest of the instruction right after the function call. Okay, but the important thing here is when we go into the loop body, we use a different trail. And here, for the function call, we use a singleton list that only containing this kappa 1. And this is because those escaping continuation introduced by block are local to a function. When we go into a new function, we can just discard the current trails. And the return instruction is interestingly just calling the last continuation in this trail. And because this is always introduced as the last element here, then we can safely call it. And we can sort of treat it loop return instruction as a syntactic sugar to BR. We're always branching to the toppest level inside of function, the jump target here, which is always the last element we have in this trail. Okay. Now we have demonstrated this core CPS semantics for WebAssembly, and this trail constructing nicely gives semantics for both block, loop, BR, call, and return. And it is also compositional in the sense that every time we call the semantic brackets, we are calling strictly a subcomponent of the syntactic construct on the left-hand side. It also tail recursive in the sense that every semantic brackets call is used in a tail position. So now, what is really good for? So of course, we can try to use the semantics to specify other extensions or other construct in WebAssembly, which we did. I will show that later. And also because the semantics is defined in a compositional way, and we can treat it as equations, and we can use it to reason about certain behavior or programs in WebAssembly. And the semantics can be implemented straightforwardly as an interpreter, basically in any function languages. And one of the things we want to do, but we haven't, is to build a partial evaluator around this semantics, because it's compositional, so it supposedly would make things much easier. So there are a couple of extensions I want to mention. We model several things. Structure loops, some of them are really hypothetic. It's not really in WebAssembly, but we just suppose we add this syntactic construct, how can we give semantics instead? The first thing I want to show is this tail call instruction. It's modeled after the current tail call proposal for WebAssembly. And by using this tail call instruction, we can explicitly enable optimizations for tail calls. And here we just model a very simple instruction, this return call. And the semantics in our framework can be straightforward because we already showed the semantics for function call. And here we just loop out the body of the function and build a new environment. But we are giving a different kind of continuation here. Instead of constructing a new continuation, coming back to the instruction of rest, we are just using the last escaping continuation on the trail, which is the theta last, and to pass into the loop body. Meaning that if there is a return instruction inside of the function body, we are returning directly to the caller of this current function frame. Basically, we're discarding this function frame and never coming back again. So we're jumping one more level here. Okay. And more interestingly here, as I mentioned, the semantics is compositional, and we can also treat it as a set of equations. We can justify the semantics I just showed here by calculating it from the semantics of return and call. And supposedly, we put a call instruction here, is call x, and right after that, we have a return instruction. So this is really a tail position of this function call. And we will do this calculation by just unfolding the semantic brackets, and firstly unfolding the semantic brackets on call x, right? And we have basically copied the definition I just showed before. And then we still have the recursive application on the return and rest, this is shown in the blue here. Then we further unfold the definition of return, showing the lower part here, and we just basically copy the semantics of return here, and we call the theta last here. And one more thing is a little bit more reasoning is guaranteed from the type system, that we can further show that this kappa 1 defined in the upper part of my slides, calling the theta last, is really just the eta expansion of theta last, because it's additionally manipulating the stack, and those manipulation can be shown to be idempotent. So we can really just inline kappa 1 here and just replace the call of kappa 1 just to theta last. And eventually we have exactly the same definition as I just showed before. So this is a powerful way to reason about semantics by equational reasoning. And another extension I want to briefly talk about is a bit hypothetic about resumable exception, or you can also think of it's really just effect handlers with just one unlabeled single operation. extend the instruction with a try-catch block, and the try block is ES1, and there's a handler in ES2, and inside of ES1, we can throw an exception or perform an effective operation. And in the catch block, we can resume back to the point where we throw this exception. So one of the example here is we have a try block, and here on line 5, we have a throw instruction, and with the error code -1, and then the control flow is transferred into the catch block. And once transferred here, on top of the stack, we have the error code and also a function value on top of the stack, and this, which is a resumption. And we can consume the error value, and then we call resume. This resume instruction, we're going back to line 6 here. And this is basically what we call resumable exception. And so the problem is, how can we express this behavior? Of course, there are already existing work on WASM effects, but here we kind of looking at traditional work in continuation passing style. And the idea is to extend our continuation with meta continuation, which means a continuation function also takes its own continuation. And here you can see the kappa continuation takes a meta continuation m count, and m count is really also the previously defined continuation. And we also have a handler value here, which can be used to handle the exceptions here. We can give those semantics here. I won't really go into details, but just to show that this something could be work here. We also have ongoing work on modeling WASM FX in this style using continuation, and we do already have a working implementation to run those programs with that WASM effects. And the idea is a bit different using meta continuation, but to use a different another trail of continuation so that we can manipulate the fragments of those continuation more easily. This handles this WASM effects is a combination of deep and shallow handlers. The formalization is still work in progress. And all those extensions we have implemented in Scala with the parser. And the current work is to validate our implementation and semantics against the official WebAssembly test suite. So some of the future work idea is we're interested in some sort of interderivation of mechanization of semantics here. And there's a well-known correspondence between big step semantics, CPS semantics, and small step reduction semantics. It would be nice to show that those semantics are really just can be interderived, for example, from the official WebAssembly specification. And the SpecTech work is also interesting. We would like to see if we can derive what we have by hand in some mechanical way using SpecTech. And a mechanization of our CPS semantics in a serial improver would be also interesting, which then we can justify our equational reasoning with a higher degree of confidence. Of course, I think there are more interesting work can be built on top of the continuation passing style. So to summarize, we have developed a CPS semantics for WebAssembly, and we use a stack of continuation to give semantics for block, loops, branching, call, and return, and the semantics compositional and tail recursive. And we have implemented this thing as a big step interpreter, but you can also use it as a compiler or transformer into a CPS form of lambda calculus. There are several possible extensions can be expressed in this framework. Some of them are hypothetic, and we showed that. Some of the ongoing work is to model WASM effects using this style. We have an accepted paper in the proceeding of trends in functional programming, and I think it's probably going to be the camera ready in February. Yeah, I think that's the end of my talk. I'm happy to take comments or questions. Yeah.
This is very nice.
Thank you.
I think you answered probably my question on your previous slide, but I just want to check.
Which one?
My question was going to be whether you proved any kind of correctness result here, and it sounds like you haven't yet.
Not yet. That's why we mentioned it would be nice to prove things in COG or any serial improvers about the correctness.
It'd be really cool if you had some sort of automatic way of taking the SpecTech specification and generating a CPS transformation
that
from
would be
that, but
nice.
that seems quite ambitious.
That's true. Yeah.
Yeah.
We're interested in looking at that. Yeah.
Hi, cool talk. I was wondering I think your first slide, you talked a little bit about like the motivation for doing this and how the small step semantics are kind of inefficient and whatnot. Are these small step semantics what WebAssembly implementations look like in practice, or is this like CPS transform? Is this compared with anything else, I guess?
So the small step semantics is not using a industrial scale implementation, but there is an official like reference interpreter implemented in this style written in Camel. But I guess I wouldn't say the performance is good. I actually hope the way if you implement it in this way would be better performance compared to the official OCaml interpreter, and with similar or even less effort.
I guess kind of a follow-up question is, what do the existing big step semantics interpreters look like?
I think Conrad has a work kind of like big step semantics for WebAssembly.
Yes, although I never tried to make it executable. That was just to power up program logic behind the scenes. All of the interpreters I've worked on have been either small step or there's this concept of pretty big step, right, that Philippa and some others here might be familiar with. I've worked on interpreters like that. I've never worked on an actual big step interpreter.
Okay, then probably this will be the first one.
Yeah, I think you can totally own that.
Yeah.
We have one more question. One more question, then I think we'll move on.
A different question. One of the extensions being worked on at the moment for WebAssembly is threads. Have you any idea how something like this would fit into threads?
I haven't looked into details of that, but I would suppose it's possible. Yeah.
Cool, thanks very much. Let's thank the speaker one last time.
Thank you.
Cool, so now we are moving into the very final session of the workshop. Thank you for bearing with us all this time. We have 2 lightning talks, and then I will give some final announcements and details of dinner plans for anyone who would like to join us afterwards. So, Philippa, you will be our first lightning talk.
What do I do?
Let's find out.
I've got that. Yeah.
That's extension, so you need to drag it across to the other. Hold it, and then that's a second
Okay,
screen.
okay.
So grab
So
it, grab it, and take it to the side. I can do it.
You too.
There we go. Yes. Yep.
Ah, I see.
It's just this
No, I
static
get it.
slide, right?
Maybe.
I mean, you don't want to.
Make it a bit bigger.
That's what I'm doing. Okay.
Thank you. So hello everybody. Last year I talked about oh, I'm not. Yes. Last. No, it's too static. Last year I talked about Wasm SpecTech at Conrad's first, how do you pronounce it? Workshop. So I thought I would just give a little update this year. So 3 minutes update. SpecTech starts with this DSL that is just dependently typed code for basically doing WASM plus annotations such that you can do lots of things automatically. Automatically being getting LaTeX, prose, an AL interpreter, and in future, because we hadn't done the work, mechanizations. So what I've just wanted to report is that we're very much on the way with the mechanizations. I had a MSc student that got a prize and did very well. And basically he went from here to ROC by looking at WASM-cert, the sort of mechanizations that we did in the past, and sort of basically copying as much as he could, given that he didn't have much knowledge, got this automatic translation of the definitions, and manually did the proofs by basically cut and pasting the proofs from WASM-cert and tinkering around a bit and making them work without much ROC expertise, which was actually rather nice. He did preservation. He only didn't do progress because he got to the end of his MSc, and I got a new MSc student who's starting the game by just doing progress that should be quite easy to do and then continuing. And in particular, the MSc student, Diego, is now a PhD student. He started early January. So what he's going to do is try to do this in really quite a principled way. So in particular, the aim is to get all these theorem provers in with different obvious suspects working on the different theorem provers. And in particular, Conrad has a student name, Antanos. Yeah. Who's just started too, and he's doing Isabel, we're doing ROC, and we're doing the same as for WASM-cert, which is trying to keep things very much in sync. We're ahead at the moment, but he's going to hurry up. But basically, we'll publish it in sync. And the idea is to how much can we do of, we have nice automatic definitions in the sense of, you know, we'll hone it and do it again to get it as good as can be. And what can we get from things like boilerplate lemmas and that sort of thing? What can we do automatically, either now or in future for the PhD? And what can we do, what do we have to do by hand? And we're going to try to push as much as we can automatically and really think about it, and also have sort of some intermediate places where, for example, ROC, Isabel, and Lean are focusing on a whole approach that goes to the various theorem provers, that basically what is that place so that the step to the theorem provers is as small as possible and things can be done once and for all. And then what can be done in the dependent type way that very much is for the actor crew, but also can be used to assess how ROC, for example, would do it if it wanted to do it in a dependent type way. And that will probably come a bit later, but that's the overall aim, to try to get this sea of mechanizations with as much done in an automatic fashion as possible, and the stuff that can't be done in an automatic fashion gets done in a sort of clean and accessible fashion, so that how much of an expert do you actually need to be in order to make this work? And in particular, we didn't have an expert doing it, but he did copy what had been done before on the WASM-cert stuff. So where do we go from here? We'll find out. I'm sure that was more than 3 minutes, but given that there's only 2 lightning talks, that's fine. Bye-bye.
I think last year I called these Thunder Talks because we extended them a little bit. Anyway, let's thank Philippa. And now Aina is our second Thunder Talk. No, yes. I mean, I can keep it if you want.
Yeah.
Is that just the you want the
Yeah.
tabs? Hold on.
Oh no. If I want to scroll, it's a little quick.
That's not too bad, right? Do you want it
That's not
further
too
in?
I think I might scroll if I need to, but.
Okay, and then there's
This is
you've
good.
got your second tab as well. There.
Yeah.
All right.
Yeah. Is this fine? The microphone? I'm not too small. Okay, good. Yeah. So hi, I'm Ina. I just want to very quickly introduce IrisWASM. I unfortunately don't have a nice figure in this paper. I might scroll up and down if people have any questions. But what is IrisWASM? It's a mechanization of WebAssembly in Iris. Iris, for those who don't know, is a higher order separation logic framework. It's implemented in Rock. And it lets you essentially instantiate any language, and you prove proof rules, and you get a separation logic. And we have done this a few years ago for WebAssembly. It's based on WASMstart, so it's very faithful to the WebAssembly 1.0 semantics. And on top of that, we defined a definition of semantic typing. So that means we interpreted all the WebAssembly types in terms of Iris propositions, so separation logic propositions. And this lets you give a very modular and useful specification of the language. And it also specifies the security properties of WebAssembly. So in particular, we also took care in defining the module system. And you get a definition of the security guarantees that WebAssembly can provide with its encapsulated modules. Now, since then, I can. Yeah. Yeah, this is maybe not so bad. Yeah, so since then, all right, it's fine. We've used IrisWASM to specify extensions of WebAssembly, and that's what I want to focus on today. That IrisWASM is a very nice way to explore new extensions, new ideas in the world of WebAssembly. And what we did last year, I think it was last year, yeah, we did that for MSWASM. So MSWASM was a proposal to extend WebAssembly with capabilities. And using IrisWASM, we gave a mechanized and, how to say, very detailed specification of MSWASM, and in particular, we could also prove that its security properties hold, which is very nice. The proof rules here, it's a bit in the middle of the paper, so I guess that this might look daunting. But it is, very faithful to WebAssembly, so it has resources for all of the components. So like the frame, the store, and here it also has the new capability store with handles. Okay, so if you're interested, you can know. Okay. Yeah, you can read more about it if you search IrisWASM or Iris MSWASM. This is the end.
Great, thanks so much.
Yeah, sorry.
So before I go to the closing of the workshop and the dinner plans, I have, because we have a little bit of time, there's one question about WebAssembly that has really tortured me over the last few years, and you are going to help me answer it if you give me 1 second to set things up.
Is this a test?
There's no wrong answer. There's maybe one wrong answer. Oh. Why don't I have control of the grabby thing? Okay, this is good enough. So I don't spoil the surprise. So I was originally going to do this as a proper Google poll, but I think we'll just do a show of hands. Okay, that did not format well. How is the A sound of WASM pronounced? Now, you would be surprised how much pain this has caused the standards body over the last few years. I think when we started WASM, we had one very clear answer. And now the community has got big enough that we don't have one clear answer anymore. So well, you're free to decide I'm pronouncing it the wrong way.
But I think people
pronounce each of those words differently.
Well, that's exactly. This is the thing. I think it started with Europeans pronouncing one A, and then Americans took that to rhyme with a different A. And then I think the Americans taught some other Europeans what they thought the sound was, and that created the third sound. So what I'm interested in, and I guess I have to maybe avoid pronouncing this word too much, but we're going to have a show of hands. Firstly, do you think this word rhymes with scam and plan? Or do you think it rhymes with star and part? Or do you think it rhymes with claw and paw? And please ignore my A. This is about your A, and whether it's the same A as the A in that word.
Put the international phonetic symbol.
I should, but I didn't. So, hands up for the first answer, scam and plan. Is that what this word rhymes with? It's close enough to a rhyme. Okay. What about the second one, star and part? Is that the same A? Okay, and what about claw and paw? Yeah, okay. So that's pretty much the distribution I expected. I counted about kind of 15 and then 7 and then 3. So I'm pretty confident when WASM was first created, we believed it was this. But it was Europeans who believed it was this. And when the Americans heard the Europeans say this A, they thought it sounded like this A. And that's how I think this happened.
But so you think it should be WASM?
Depends on what your A is, but yes.
No, I'm not asking, no.
Do we have,
that's not the answer.
do we have good examples of the three? Like, do we have an American?
Can you say one of the 3 ways?
Yeah.
Okay, well, I'll say it my 3 ways, but I think we should get if we wanted to be really scientific about this, we'd get a representative of each belief to say what they thought. But maybe that will take a little too long. I'm not trying to settle the debate here, but I do want to at least get a survey of the room, and I'm reassured that I'm correct in thinking we have had a divergence, because we have had representatives of each 3 pronunciations show up here. Sorry, I saw a hand at the back. Exactly. Oops.
Starting like a meta question, which is there, raise your hand if you agree that the first option causes WASM to rhyme with CHASM, like a big hole in the ground that you might.
Yes, it's yes.
Does the first option? Does everyone agree that the first option rhymes with that word? Yeah. Okay, so at least that's very clarifying.
You see, actually, you're being very smart, because I originally did want to put that word here, and then I realized I couldn't find precise rhymes for the other 2 options. So I decided I'd make them all equally slightly off. But okay, I don't think we can do anything more here. Feel free to argue over this for the rest of your lives, but I'm glad to have at least vindicated myself in realizing there is a genuine split in the world. Okay, so very last matter of business is the dinner plan. Please bear with me for a couple of seconds while I get the dinner plans on screen, and then I'll describe them to you. Chrome has given up. Okay, you know what? I'm just going to do it this way. I was thinking about that joke as well, but don't worry. Okay, so the plan is to go to this restaurant, Venice, and I'll bring up the full address in a second, at 6:30 p.m. The restaurant has asked that we give rough numbers half an hour before we arrive. So what I would like now is, if you are interested in showing up, please give me a show of hands. And if you want to bring someone else who is not in this room, please come and talk to me after I close the session. So first, can I get a rough show of hands? Does anyone want to come to the dinner here at 6:30? Okay, everyone needs to keep their hands up now and not change anything. Okay, perfect. Thank you so much. And again, if anyone would like to invite someone who's not here, that's fine. Just come to me so I can get the numbers involved. All right. Thank you so much for coming to this, the second edition of the WebAssembly Workshop. We are hoping to run future editions, so please spread the word when the adverts for those go out. But for now, thank you again for coming, and hopefully see you all again next year.
Thank you, Conrad. Awesome as always.